At the center of the Milky Way, approximately 26,000 light-years from Earth, is a compact object identified as Sagittarius A-star, the galaxy's central supermassive black hole. Its presence has been confirmed through long-term measurements of stellar orbits, which show stars moving at velocities exceeding 5,000 miles per second around a common focal point. These observations indicate a gravitational mass of roughly 4 million solar masses, confined within a region smaller than Mercury's orbital radius. Historically, Sagittarius A-star has exhibited relatively low activity compared to other galactic nuclei, with only sporadic infrared and X-ray flaring. In 2023, the James Webb Space Telescope conducted high-resolution infrared observations of the galactic center, enabling detailed analysis of gas dynamics and magnetic structures in the immediate environment of the black hole. The findings prompted extensive follow-up analysis within the astrophysical community. If confirmed, the results suggest that Sagittarius A-star operates under physical conditions not fully accounted for by current models, with potential implications for black hole behavior in galactic centers. Discovery of a compact radio source. The Milky Way is a barred spiral galaxy stretching roughly 100,000 light-years from edge to edge, containing between 200 and 400 billion stars bound together by gravity and dark matter. Our Sun sits in one of the spiral arms, about 2/3 of the way out from the galactic center, orbiting the core once every 230 million years. For most of human history, we had no idea what lay at the very center of this cosmic whirlpool. The galactic core is hidden behind thick clouds of dust and gas that block visible light, rendering the heart of our galaxy invisible to optical telescopes. But radio waves and infrared light can penetrate this dusty veil. In the 1970s, astronomers using radio telescopes detected a powerful radio source at the exact center of the galaxy. They designated it Sagittarius A-star, named after the constellation Sagittarius, where it appears in our sky. The asterisk indicated something special, a compact object unlike anything else in that region. Initial measurements showed it was incredibly small for something emitting such strong radio signals, less than 1 astronomical unit across, smaller than Earth's orbit around the Sun. For years, scientists debated what Sagittarius A-star actually was. Some proposed a cluster of neutron stars packed tightly together. Others suggested a dense cloud of dark matter. But the leading theory, supported by increasingly precise observations, was that it had to be a black hole. Nothing else could explain the extreme density and intense gravitational effects observed in that region. The breakthrough came in the 1990s when astronomers began tracking individual stars orbiting near the galactic center. Using telescopes equipped with adaptive optics to correct for atmospheric distortion, researchers identified a star designated S2 that orbits incredibly close to Sagittarius A-star. S2 completes one full orbit in just 16 years, compared to our Sun's 230 million year orbit. By carefully measuring S2's position over many years, astronomers could calculate its orbital velocity and distance from the central object. The numbers were staggering. At its closest approach, S2 whips around Sagittarius A-star at over 5,000 miles per second, nearly 3% the speed of light. Using Kepler's laws of orbital motion, the same principles that govern planets orbiting our Sun, scientists calculated the mass of the central object. The answer kept coming back the same, approximately 4.15 million times the mass of our Sun, with an uncertainty of only a few percent. This was confirmed by tracking dozens of other stars in similar orbits. All the data pointed to the same conclusion. There is a supermassive black hole at the center of our galaxy, and we have been orbiting it for billions of years. The term supermassive distinguishes these galactic monsters from smaller stellar mass black holes formed when individual massive stars collapse. Stellar black holes typically weigh between 5 and 100 solar masses. Supermassive black holes weigh millions or billions of times more. Almost every large galaxy contains one at its core, suggesting these objects play a fundamental role in galaxy formation and evolution. The Milky Way's black hole is actually on the smaller end of the supermassive scale. Andromeda's central black hole weighs about 140 million solar masses. Some galaxies harbour black holes exceeding 10 billion solar masses. Despite its enormous mass, Sagittarius A-star is surprisingly compact. The event horizon, the boundary beyond which nothing can escape, has a diameter of about 24 million kilometres. That is large enough to swallow our Sun and still have room left over, but incredibly small, considering it contains over 4 million stars worth of matter. This extreme density creates gravitational fields so intense they warp space-time itself. Light passing near the black hole bends. Time dilates. The rules of physics as we experience them on Earth break down. For decades, Sagittarius A-star was classified as a remarkably quiet black hole. Unlike the brilliant quasars visible across the universe, active supermassive black holes that shine brighter than entire galaxies as they devour enormous amounts of matter. Our galactic center is subdued. It does flare occasionally, briefly brightening in X-rays and infrared as it consumes a gas cloud or tears apart a star that wandered too close. But most of the time, it is almost dormant, barely feeding at all. This quietness is actually unusual. Given the number of stars, gas clouds and debris in the galactic center, astronomers expected Sagittarius A-star to be more active. Something seems to be preventing material from falling efficiently into the black hole. Perhaps magnetic fields are providing resistance. Perhaps the gas is too hot and diffuse to accumulate effectively. Or perhaps we are simply observing it during a quiet phase, and it was far more active in the past. The Event Horizon Telescope provided our first actual image of Sagittarius A-star in 2022. Using a network of radio telescopes spread across the entire planet, functioning together as an Earth-sized telescope, researchers captured the shadow of the black hole against the glowing ring of hot gas orbiting around it. The image showed a dark circular region surrounded by a bright, slightly asymmetric ring. This was the photon sphere, the region where light itself orbits the black hole before either escaping or falling in. The image confirmed predictions from general relativity and provided the first direct visual proof that Sagittarius A-star is indeed a black hole. But the Event Horizon Telescope operates at radio wavelengths. It revealed the black hole's shadow and immediate surroundings, but could not penetrate deeper into the surrounding structures or see the cooler material lurking in the galactic center. That required different eyes, infrared eyes, the kind possessed by the James Webb Space Telescope. When Webb turned towards Sagittarius A-star in 2023, it saw far more than anyone expected. Initial infrared imaging of the galactic center. The James Webb Space Telescope represents humanity's most ambitious effort to observe the infrared universe. Launched on December 25, 2021, Webb orbits the Sun at a point called L2, about 1 million miles beyond Earth, where it remains in shadow, shielded from the heat and light of the Sun, Earth, and Moon. This distant location and its massive sun shield keep the telescope's instruments incredibly cold, essential for detecting faint infrared signals from across the universe. Webb's primary mirror measures 6.5 meters across, composed of 18 hexagonal segments made of beryllium coated in gold. Gold is an excellent infrared reflector, and the segmented design allowed the mirror to fold up during launch and deploy once in space. This mirror is nearly 3 times larger than Hubble's, giving Webb far greater light collecting power and the ability to see fainter and more distant objects. But size is only part of Webb's advantage. The real breakthrough is its infrared sensitivity. Infrared light has longer wavelengths than visible light. Humans cannot see it, but we can feel it as heat. Cool objects like planets, dust clouds and forming stars emit primarily in infrared. By observing in this part of the spectrum, Webb can see through cosmic dust that blocks visible light completely. This makes it perfect for studying the galactic center, which is shrouded in dust so thick that visible light telescopes can barely penetrate it. What appears as a dark, obscured region in optical images blazes with light in Webb's infrared view. Webb carries 4 main instruments. The near-infrared camera, or NIRCAM, captures sharp images of stellar populations and structures. The near-infrared spectrograph, NIRSPEC, splits light into its component wavelengths, revealing the chemical composition and motion of objects. The mid-infrared instrument, MIRE, detects cooler objects and dust. And the fine guidance sensor combined with the near-infrared imager and slitless spectrograph, FGS/NIRISS, helps the telescope maintain precise pointing while also conducting science observations. Together, these instruments provide unprecedented views of the universe in infrared light. When planning observations of Sagittarius A-star, astronomers face significant challenges. The galactic center is one of the most crowded regions of sky, packed with millions of stars, dense gas clouds, and intense radiation. The black hole itself is incredibly compact, requiring precise targeting and long exposure times to capture useful data. Additionally, Sagittarius A-star is variable. It flares unpredictably, sometimes brightening by factors of 100 or more within hours. This variability makes it difficult to predict what Webb would see during any given observation. The observations began in April 2023, with Webb dedicating multiple sessions to the galactic center. NIRCam captured wide-field images showing the distribution of stars and dust, while MIRI focused on the cooler material surrounding the black hole. NIRSpec collected spectra from gas clouds in the accretion zone, measuring their velocities and compositions. The data streamed back to Earth over several months as Webb continued its observations, building up a comprehensive infrared portrait of the galactic core. Initial processing of the images revealed structures that were vaguely familiar but far more detailed than anything seen before. Filaments of hot gas snaked through the region. Dense clouds of dust glowed with infrared radiation. Stars clustered near the black hole shone brightly, their heat signatures standing out against the cooler background. But as astronomers dug deeper into the data, particularly the spectroscopic measurements and time series observations, they began noticing anomalies. The gas in the accretion disk around Sagittarius A-star was not moving the way models predicted. Doppler measurements showed material orbiting at different speeds than gravitational simulations suggested it should. Some regions were moving faster, as if being accelerated by an additional force. Other regions appeared almost stationary, as if held in place against the pull of gravity. This made no sense. Black holes are remarkably simple objects governed by well-understood physics. Their gravity should produce predictable effects on surrounding material. Temperature measurements added to the confusion. The accretion disk should have a smooth temperature gradient, hottest near the black hole and cooling with distance. Webb's data showed irregular hotspots scattered throughout the disk, regions heating to millions of degrees for no apparent reason. These hotspots appeared and disappeared over timescales of hours, far too quickly to be explained by standard accretion physics. Something was injecting energy into the gas in unpredictable bursts. Then there were the magnetic field measurements. By analyzing the polarization of infrared light from the accretion disk, astronomers could infer the structure of magnetic fields threading through the gas. Magnetic fields play a crucial role in accretion, helping transport angular momentum and allowing material to spiral inward toward the black hole. The fields around Sagittarius A-star were stronger than expected, but more disturbing was their configuration. The field lines were twisted into complex, chaotic patterns that changed significantly between observations taken just days apart. One particular feature caught everyone's attention. Webb detected a spiral structure in the inner accretion disk, visible in both NIRCAM and MIRI data. The spiral appeared to be a density wave, a region where gas was compressed into a higher density pattern that rotated around the black hole. Spiral density waves are known to exist in galaxies and planetary rings, but the spiral around Sagittarius A-star was far more tightly wound and appeared to be growing stronger with each observation. By comparing data from different sessions, astronomers calculated that the spiral was intensifying at an accelerating rate. Theoretical models were run to explain the spiral. Perhaps it was a temporary perturbation caused by a star or gas cloud falling into the accretion disk. Perhaps it was a resonance phenomenon related to the black hole's rotation. Perhaps it was an instability in the disk itself, a sign that the accretion flow was transitioning from one state to another. None of these explanations fit the data perfectly. The spiral was too strong, too persistent, and too well organized to match standard predictions. It looked like something was actively driving it, maintaining its structure against the chaotic turbulence that normally characterizes accretion disks. The scientific papers began appearing in late 2023 and early 2024. Titles like Anomalous Accretion Dynamics in Sagittarius A-star and Unexplained Magnetic Field Evolution at the Galactic Center hinted at the mystery unfolding. The astronomy community debated whether these observations represented genuine new physics or simply revealed limitations in our models. After all, black hole accretion is incredibly complex, involving magnetohydrodynamics, general relativity, and plasma physics. Perhaps the simulations were missing key processes, but as more data arrived and more researchers analyzed the Webb observations, a consensus began forming. Sagittarius A-star was not behaving like other quiet supermassive black holes. Something unusual was happening, and whatever it was seemed to be accelerating. The question was no longer whether something strange was occurring. The question was what it meant. Stellar mass loss and accretion processes at the galactic center. The region immediately surrounding Sagittarius A-star is one of the most extreme environments in the galaxy. Within a few light years of the black hole orbit some of the fastest moving stars known to science. These are not ordinary stars. They are massive, luminous, and incredibly young by astronomical standards. Their presence so close to the black hole is itself a puzzle that has challenged astronomers for decades. The star designated S2, also known as S02, is the most famous of these objects. It is a blue main sequence star, roughly 15 times the mass of our Sun, burning hot and bright with a surface temperature around 20,000 Kelvin. S2 orbits Sagittarius A-star once every 16.05 years in a highly elliptical orbit. At its farthest point, it is about 1,500 astronomical units from the black hole. At its closest approach, called periastron, it plunges to within 120 astronomical units, less than 4 times the distance from our Sun to Neptune. During periastron, S2 reaches velocities exceeding 7,600 kilometers per second, about 2.5% the speed of light. At these speeds, relativistic effects become measurable. Time dilation causes clocks on S2 to run slower than clocks farther from the black hole. Gravitational redshift causes light leaving S2 to lose energy, climbing out of the intense gravitational well. These effects have been measured and match Einstein's general relativity predictions with remarkable precision, providing some of the best tests of relativity in strong gravitational fields. S2 is not alone. Dozens of stars orbit within a few light years of Sagittarius A-star. Astronomers have designated them S1, S4, S5, and so on, with each number representing a different star tracked over multiple years. Some orbit in periods as short as 10 years. Others take centuries to complete one revolution. By studying their orbits, astronomers have refined the mass measurement of Sagittarius A-star to extraordinary precision. 4.154 million solar masses, with an uncertainty of less than 1%. But here is the mystery. These stars should not exist where they are. Stars form from clouds of gas and dust. The intense tidal force is near a supermassive black hole, would shred any gas cloud trying to collapse into a star. The region within a few light years of Sagittarius A-star should be a stellar desert, devoid of star formation. Yet not only are there stars present, but they are young stars less than 10 million years old. They formed relatively recently, which means somehow star formation occurred in the most hostile environment imaginable. Several theories attempt to explain this paradox. One suggests the stars formed farther out and migrated inward through dynamical interactions with other stars. Gravitational slingshots could have kicked them into tighter orbits around the black hole. Another theory proposes the stars formed in a massive accretion disk around the black hole billions of years ago, when it was more actively feeding. The disk would have been dense enough and extended enough for stars to form despite the extreme environment. Once formed, these stars survived billions of years in their close orbits. A third, more radical theory suggests the stars formed elsewhere in the galaxy and were captured by the black hole. Binary star systems could have wandered too close, with one star captured and the other ejected at high velocity. Over time, the galactic center would accumulate a population of captured stars, explaining their presence near Sagittarius A-star. James Webb's observations added crucial new data to this puzzle. By observing the stars in infrared, Webb detected cooler companions around some of the bright stars. These companions are red giants or dwarf stars that were invisible or barely visible in previous observations. Their presence suggests that at least some of the S stars are part of binary or multiple star systems, supporting the capture theory. If these systems formed elsewhere and were captured as units, some might retain their companions despite the disruptive tidal forces. Webb also measured the chemical composition of the S stars through spectroscopy. The abundances of elements like iron, oxygen, and carbon provide clues about where and when the stars formed. The data showed that the S stars have metallicities similar to stars in the galactic bulge, the central region of the Milky Way. This suggests they formed locally rather than in the outer galaxy, supporting theories that they either formed in place or migrated inward from the bulge region. But the most startling discovery came from time series observations. By imaging the same stars multiple times over several months, Webb detected something unexpected. Several of the S stars showed variability in their infrared brightness. This variability was not due to the stars themselves pulsating or changing. Instead, it appeared to be caused by obscuring material passing in front of them. Clouds of dust or gas were periodically blocking the starlight. Analyzing the pattern of obscuration revealed that this material was not randomly distributed. It appeared to be organized into structures, possibly filaments, or streams of gas and dust orbiting the black hole at distances comparable to the S star orbits. This material had been too faint and diffuse to detect before, but Webb's sensitivity revealed its presence. The implications were profound. If there is significantly more gas and dust near Sagittarius A-star than previously realized, it could change our understanding of how the black hole feeds and how the central environment has evolved. The discovery raised immediate questions. Where did this obscuring material come from? How much of it exists? Is it falling into the black hole, and if so, at what rate? Could it be related to the anomalous accretion dynamics Webb detected? Researchers began constructing models to explain the observations. Perhaps a gas cloud had recently been disrupted near the black hole, creating a temporary increase in material availability. Perhaps the obscuring structures were remnants of a star that had been tidally destroyed years ago. One star in particular drew intense scrutiny. Designated S62, this star has an orbital period of only 9.9 years, making it one of the fastest orbiting stars known around any supermassive black hole. S62 reaches periastron speeds exceeding 8% the speed of light, making it an even better laboratory for testing relativity than S2. Webb's observations caught S62 during a close approach in 2023, revealing that it is surrounded by an extended envelope of material, possibly a stellar wind being stripped away by the black hole's tidal forces. The interaction between S62 and the black hole provided a real-time view of how stars lose mass in extreme environments. As S62 swung around periastron, its outer atmosphere was pulled toward the black hole, creating a stream of gas flowing from the star into the accretion disk. Webb tracked this stream across multiple observations, measuring its temperature, velocity, and composition. The data showed the stream was hotter and denser than expected, suggesting it was being heated by some additional mechanism, possibly magnetic reconnection or shock waves in the surrounding gas. This stellar stripping process has significant implications for feeding the black hole. If multiple stars near Sagittarius A-star are losing mass to tidal interactions and stellar winds, they collectively provide a steady stream of material to the accretion disk. Over millions of years, this could add up to a substantial amount of mass, even if each individual star contributes only a small fraction of its total mass. The black hole does not need dramatic events like the tidal disruption of entire stars to maintain a low level of activity. The accumulated winds and tidal stripping from dozens of close orbiting stars might be enough. The S-stars are not just traces of the black hole's gravitational field, they are active participants in its ecosystem, feeding it material and responding to its influence. Webb's observations revealed this ecosystem in unprecedented detail, showing that the region around Sagittarius A-star is far more dynamic and complex than previously understood. And at the heart of this complexity sits the black hole, quietly accumulating mass, its gravity warping space and time, pulling everything inexorably inward. Structure and physics of black hole. Accretion disks. Black holes do not consume matter directly through some sort of cosmic vacuum effect. Material must lose angular momentum to fall inward, and this process creates an accretion disk, a swirling disk of gas and dust spiraling gradually toward the event horizon. Accretion disks are common around black holes, from stellar mass black holes in binary systems to supermassive black holes in galaxy centers. The physics of accretion is well studied, with detailed models describing how material behaves as it falls inward, or so astronomers thought. Webb's observations of the accretion disk around Sagittarius A-star revealed structures and behaviors that do not fit standard accretion theory. The disk is far more complex, far more active, and far stranger than models predicted for a black hole that is supposed to be mostly dormant. The first surprise came from measuring the disk's size and temperature distribution. Previous observations suggested the accretion disk extended perhaps a few dozen astronomical units from the black hole, with temperatures decreasing smoothly outward from the hottest regions near the event horizon. Webb's infrared data painted a different picture. The disk is larger than expected, extending out to at least 100 astronomical units, roughly twice the distance from our Sun to Pluto. This extended disk glows primarily in mid-infrared wavelengths, indicating temperatures of hundreds to a few thousand Kelvin. Closer to the black hole, the disk transitions to near-infrared and eventually into X-ray wavelengths as temperatures climb into the millions of degrees. But the transition is not smooth. Webb detected multiple temperature zones with sharp boundaries between them, as if the disk consists of distinct regions with different physical properties. Spectroscopic measurements revealed the chemical composition of the disk material. It contains ionized hydrogen and helium, as expected, but also heavier elements like carbon, oxygen, nitrogen, and iron. The presence of these elements indicates the gas originated from stellar sources, either stellar winds from nearby stars or debris from stars disrupted by the black hole's tidal forces. The abundances of certain elements, particularly iron and nickel, suggest some of the material comes from supernova remnants or exploded white dwarf stars, enriching the disk with metals. The disk is also stratified vertically. It is not a thin, flat structure, but has significant thickness, with gas extending above and below the midplane. This vertical structure creates a complex three-dimensional flow pattern. Material in the upper layers of the disk moves on different trajectories than material in the midplane, with some gas falling inward, while other gas is being pushed outward by radiation pressure and magnetic forces. Webb's spectroscopy could distinguish between these layers by measuring Doppler shifts, revealing the full three-dimensional velocity structure of the disk. But the most perplexing feature is the spiral structure mentioned earlier. Webb's images clearly show a two-armed spiral pattern in the inner disk, extending from about 10 to 50 astronomical units from the black hole. The spiral rotates, completing one revolution in approximately 60 days based on observations taken over several months. This rotation rate corresponds to material orbiting at roughly the expected velocity for that distance, suggesting the spiral is a fixed pattern in the disk, rather than material actually spiraling inward along those arms. Spiral density waves are well known in other astrophysical contexts. Saturn's rings display spirals driven by the gravitational influence of moons. Spiral galaxies themselves have arms that are density waves rather than fixed structures. The mechanism for creating these patterns involves resonances, where the orbital period of material matches some multiple of a driving frequency. In Saturn's rings, the moons provide the driving force. In spiral galaxies, the gravitational potential of the bar or bulge creates the resonance. What is driving the spiral in Sagittarius A-star's accretion disk? Several possibilities exist. If the black hole is rotating, which it almost certainly is, its rotation could create a pattern in the surrounding space-time called frame dragging. This effect, predicted by general relativity, causes space-time itself to be pulled around by the rotating mass. Material orbiting in this dragged space-time experiences additional forces that could seed a spiral pattern. Alternatively, a massive object orbiting within the disk, perhaps a stellar mass black hole or neutron star, could gravitationally perturb the gas and create spiral arms. A third possibility is that the spiral is a precessing instability in the disk itself. Accretion disks are not stable structures. They are prone to various instabilities driven by magnetic fields, radiation pressure, and differential rotation. Under certain conditions, these instabilities can organize into coherent patterns that persist for extended periods. The spiral in Sagittarius A-star's disk might be such an instability, reflecting some fundamental property of how matter accretes onto a rotating black hole. Webb's repeated observations allowed astronomers to track how the spiral evolves over time. The pattern is not static. The arms appear to be tightening, winding more tightly around the black hole with each observation. The amplitude, the difference in density between the spiral arms and the interarm regions, is also increasing. This suggests the spiral is growing stronger, extracting energy from the disk's rotation and transferring it into the pattern itself. If this continues, the spiral could eventually become unstable and either dissipate violently or transition into a different configuration. Temperature measurements within the spiral revealed another anomaly. The gas in the spiral arms is hotter than the gas between the arms, opposite what you would expect if the spiral was simply a compression wave. Compression should heat gas, making the arms hotter, but the excess heating Webb detected is far greater than compression alone can explain. Something is preferentially heating the spiral arms, injecting energy into those specific regions. Possible mechanisms include magnetic reconnection, where tangled magnetic field lines snap and release energy, or shock waves generated by the spiral motion itself. Webb also detected variability in the disk on short timescales. Comparing images taken hours apart showed bright flares appearing and disappearing at random locations in the inner disk. These flares, visible in near-infrared wavelengths, indicate sudden heating of gas to extremely high temperatures, tens of thousands of Kelvin or more. The flares last anywhere from minutes to hours before fading. Their random distribution suggests they are not related to organized structures like the spiral, but instead represent chaotic turbulence or magnetic instabilities in the disk. The accretion rate, how much mass is actually falling into the black hole per year, is difficult to measure directly. Astronomers estimate it by observing the total luminosity emitted by the accretion disk and working backward to calculate how much mass must be accreted to produce that luminosity, assuming a certain efficiency for converting mass into radiation. For Sagittarius A-star, the estimated accretion rate is extremely low, perhaps 10 to the -7 to 10 to the -9 solar masses per year. That is less than 1 Earth mass per year falling into a black hole weighing 4 million times the mass of the Sun. This incredibly low accretion rate explains why Sagittarius A-star is so quiet compared to actively feeding black holes. It is essentially starving. The question is why. There is plenty of gas in the galactic center and stars nearby are losing mass through winds. That material should eventually find its way to the black hole. Something must be preventing efficient accretion, either removing angular momentum too slowly or providing resistance that keeps material from falling in. One proposed explanation involves the gas being too hot. In a phenomenon called advection-dominated accretion, gas falling toward the black hole can be heated so efficiently that it becomes buoyant and puffs up rather than settling into a thin disk. This hot, inflated flow accretes very slowly because the gas has so much energy it partially resists the pull of gravity. Sagittarius A-star might be in this regime, with the bulk of the accretion occurring through an inefficient, puffed-up flow rather than a thin, efficient disk. Webb's observations of the temperature structure lend some support to this idea. The gas is indeed hot, with temperatures far exceeding what would be expected in a standard thin disk. But the presence of the spiral and other organized structures suggests the disk is not completely dominated by hot, chaotic gas. There seems to be a cooler component, perhaps closer to the midplane, where the spiral resides, surrounded by a hotter, more diffuse atmosphere. This two-component structure complicates the picture and makes it harder to determine what regulates the accretion flow. The discovery of the extended accretion disk and its anomalous properties has profound implications. If Sagittarius A-star has more material available in its vicinity than previously realized, it could potentially transition to a higher accretion state. A small increase in the accretion rate could make the black hole significantly more luminous, transforming it from a quiet, barely detectable object into a moderately active galactic nucleus. Whether such a transition is likely or even possible given the current conditions is a matter of intense debate among researchers analyzing Webb's data. Polarization and spectroscopic probes of magnetized plasma. Magnetic fields are invisible architects of the universe. They channel plasma, accelerate particles, and transport energy across vast distances. Around black holes, magnetic fields play an absolutely critical role in the accretion process. Without them, gas would not lose angular momentum efficiently, and accretion would proceed far more slowly. The structure and strength of these fields determine how a black hole feeds and how it impacts its surroundings. Observing magnetic fields directly is impossible. They do not emit light, but their effects on charged particles can be detected through several methods. Polarization is the primary tool. Light waves oscillate, and the plane of oscillation can be oriented in specific directions. When light passes through a magnetized plasma, its polarization is affected. By measuring the polarization of light from an accretion disk, astronomers can infer the structure and strength of the magnetic field threading through the plasma. The Event Horizon Telescope's 2022 image of Sagittarius A-star included polarization measurements, revealing that strong magnetic fields exist in the immediate vicinity of the black hole. The fields appeared to be organized into loops or spirals, consistent with theoretical predictions for magnetized accretion flows. But the resolution of those observations was limited. The Event Horizon Telescope could only probe the very innermost regions within a few Schwarzschild radii of the event horizon. Webb's observations extend this view outward, revealing the magnetic field structure over a much larger volume. Webb does not measure magnetic fields directly, but it observes phenomena caused by magnetic fields. Certain infrared emission lines are produced by ions in excited states, and the strength and shape of these emission lines depend on the local magnetic field. By analysing the spectral profiles of these lines, astronomers can estimate field strengths. The data from Sagittarius A-star revealed fields on the order of tens to hundreds of milligauss in the inner accretion disk, far stronger than the interstellar magnetic field elsewhere in the galaxy, which is typically a few microgauss. These strong fields are expected. As gas falls toward a black hole and compresses, any magnetic field embedded in the gas compresses as well, increasing in strength. The process is analogous to squeezing a rubber band. The tighter you pull, the stronger the tension. In the case of an accretion disk, the compression occurs in multiple dimensions as gas spirals inward and flattens into a disk, leading to dramatic amplification of magnetic fields. Models predict that fields should reach milligauss or even Gauss levels near black holes, and Webb's observations confirm this. But magnetic field strength is only part of the story. The configuration of the field, how the field lines are organized and where they point, is equally important. Webb's polarization measurements suggested the field near Sagittarius A-star is not orderly. Instead of neat spirals or loops, the field appears highly tangled, with regions of chaotic, disordered magnetic structures. This is consistent with turbulence in the accretion disk. As gas swirls and collides, magnetic field lines get stretched, twisted, and reconnected in complex ways. Magnetic reconnection is a process where oppositely directed field lines come together and snap, releasing vast amounts of stored magnetic energy in a fraction of a second. On the Sun, magnetic reconnection drives solar flares, explosions that release energy equivalent to millions of nuclear bombs. Around black holes, reconnection events can be even more energetic, heating gas to millions of degrees and accelerating particles to nearly the speed of light. The bright flares Webb detected in the accretion disk might be signatures of magnetic reconnection events, brief but violent energy releases scattered throughout the turbulent plasma. One particularly intriguing observation involved tracking changes in the magnetic field over time. By comparing polarization data from observations taken weeks apart, researchers noticed that the overall field structure in the inner disk had changed significantly. Features that appeared in the first observation had disappeared or moved in the second. This rapid evolution suggests the magnetic field is not in a steady state. It is dynamic, constantly reconfiguring itself in response to the turbulent motions of the gas. The implications are significant. A rapidly changing magnetic field can drive additional variability in the accretion flow. It can create instabilities that cause gas to fall inward in bursts rather than steadily. It can also transport angular momentum more efficiently, allowing material to spiral toward the black hole faster than would be possible with a static field. The chaotic magnetic environment around Sagittarius A-star might explain why the accretion disk behaves so erratically, with flares and variability that do not match simple theoretical predictions. Webb also detected evidence for magnetic field amplification through a process called the magnetorotational instability, or MRI. This instability arises in differentially rotating disks, where inner regions orbit faster than outer regions. Magnetic field lines threading through such a disk get stretched and amplified, extracting rotational energy from the disk and converting it into magnetic energy. The MRI is thought to be the primary mechanism that allows accretion disks to lose angular momentum and accrete efficiently. Without it, gas would simply orbit indefinitely without falling in. The spectroscopic signatures of the MRI are subtle. They manifest as specific velocity patterns in the gas, with correlated fluctuations in radial and azimuthal velocities. Webb's high-resolution spectroscopy captured these patterns, confirming that the MRI is active in the inner disk. But the amplitude of the fluctuations is larger than standard MRI theory predicts, suggesting the process is more violent than expected, possibly enhanced by the black hole's rotation or by additional physics not included in standard models. The magnetic field also appears to be launching material outward from the disk. Jets and outflows are common features of accreting black holes. High-energy plasma can be channeled along magnetic field lines and ejected from the poles of the black hole at velocities approaching the speed of light. Sagittarius A-star has shown hints of such outflows in previous X-ray observations, but they were weak and difficult to characterize. Webb's infrared observations provided a new perspective, detecting warm gas flowing outward from the inner disk at velocities of several hundred kilometers per second. This outflow is not a full-fledged jet. It is more diffuse, more like a wind, but it carries significant mass and energy away from the black hole, comparable to the amount of material accreting inward. In other words, for every gram of gas falling into Sagittarius A-star, roughly an equal amount is being blown back out. This creates a self-regulating feedback loop. The more the black hole feeds, the stronger the outflow, which in turn limits how much additional material can fall in. This might be why Sagittarius A-star remains so quiet despite the availability of gas in the galactic center. The connection between the magnetic field and the outflow is direct. The field lines act like rails, guiding the plasma as it accelerates outward. Energy is extracted from the rotating magnetic field and transferred to the gas, speeding it up and pushing it away from the black hole. The exact mechanism is still debated. Some models invoke radiation pressure, where photons emitted by the hot inner disk push on the gas. Others rely on magnetic pressure, where the field itself exerts force on the plasma. Webb's data suggests both processes are at work, contributing in different regions of the disk and outflow. The chaotic magnetic field raises a troubling question. If the field is so tangled and disorganized, how can it produce organized structures like the spiral density wave? Shouldn't turbulence destroy any large-scale coherence? The answer appears to involve a process called dynamo action, where turbulent motions paradoxically generate large-scale magnetic fields. Small-scale turbulence creates random magnetic loops and eddies. But when these interact in a rotating disk, they can produce a net field that threads the entire disk. This dynamo-generated field is what drives the spiral and other organized features, even as small-scale chaos persists. Understanding the magnetic field around Sagittarius A-star is crucial for understanding how it feeds and evolves. The field controls the accretion rate, launches outflows, and determines how energy is dissipated in the disk. Webb's observations have revealed a magnetic environment far more complex and dynamic than anticipated, challenging theorists to develop more sophisticated models. The simple picture of a smooth, steady accretion disk dominated by gravity has been replaced by a portrait of magnetic chaos, where fields twist, reconnect, and drive turbulent flows that barely allow the black hole to feed at all. Filaments, streams, and the aftermath of disruption. Sagittarius A-star does not only feed on the slow trickle of gas from the accretion disk. Occasionally, larger clumps of material fall toward the black hole, providing brief but intense feeding episodes. These events, where gas clouds or even entire stars approach close enough to be disrupted by tidal forces, offer rare opportunities to study black hole feeding in real time. Webb's observations caught at least one such event in progress, revealing details never before seen. Gas clouds in the galactic center typically orbit at safe distances, their internal gravity and pressure holding them together against the weak tidal forces at those radii. But gravitational interactions with nearby stars or the black hole itself can perturb their orbits, sending them onto trajectories that bring them perilously close to Sagittarius A-star. As a cloud approaches, the tidal forces strengthen. The side of the cloud facing the black hole experiences stronger gravity than the far side, creating a differential force that stretches the cloud along the radial direction and compresses it perpendicular to that direction. This process, called spaghettification when applied to solid objects, turns gas clouds into long, thin filaments that stream toward the black hole. In 2011, astronomers discovered a gas cloud designated G2 on a collision course with Sagittarius A-star. G2's orbit was predicted to bring it within about 3,000 Schwarzschild radii of the black hole in mid-2014, close enough that tidal disruption seemed inevitable. Excitement built as telescopes worldwide prepared to observe what was expected to be a spectacular feeding event. The hope was that G2 would dump a significant amount of material into the black hole, triggering a bright flare that could be studied across multiple wavelengths. When the moment arrived, however, the results were anticlimactic. G2 survived its close approach largely intact, producing only a modest increase in emission. The cloud appeared to be more resilient than expected, possibly because it was not just a cloud, but contained a hidden star at its core that held it together through the encounter. Webb's observations a decade later revealed the aftermath. G2 is now stretched into a long filament extending over several light months, but it has not been completely destroyed. The filament continues to orbit the black hole, slowly spiraling inward as it loses energy through interactions with other gas in the region. Webb tracked the filament's motion and measured its temperature and velocity, finding that it is gradually heating up as it compresses. Within a few decades, the material from G2 will likely rain down onto the accretion disk, finally contributing to the black hole's diet years after the initial encounter. But G2 is not the only such object. Webb detected multiple smaller gas clouds and filaments in the vicinity of Sagittarius A-star, some approaching on orbits similar to G2's, others already in the process of being tidally shredded. One of these, tentatively designated G3 by researchers analysing the data, appears to be on a trajectory that will bring it even closer to the black hole than G2 reached. G3 is smaller and less massive, but its closer approach means tidal forces will be stronger. Predictions suggest G3 will be completely disrupted when it reaches periastron in the late 2020s, potentially providing the feeding event astronomers hope to see with G2. Spectroscopic analysis of G3 revealed it is composed primarily of ionized hydrogen and helium with traces of heavier elements. Its velocity relative to the black hole is several thousand kilometers per second, indicating it originated from a region with higher orbital velocities, possibly from closer to the galactic center. How it ended up on such an eccentric orbit remains unclear. Perhaps it was ejected by a stellar encounter, or perhaps it is debris from a previous tidal disruption event, now falling back toward the black hole after being flung outward years ago. Webb also observed what appears to be the remnant of an older disruption event. A diffuse arc of glowing gas curves around one side of the accretion disk, its shape suggesting it was once a coherent cloud that was torn apart and now forms a partial ring orbiting the black hole. The gas in this arc is moving too fast to remain bound to the black hole indefinitely. Over the next few thousand years, it will either fall inward and be accreted, or escape the system entirely, depending on how much additional energy it gains from interactions with other material. These transient feeding events, though brief on astronomical timescales, can significantly impact the black hole's activity level. Even a small gas cloud weighing a few times the mass of Earth can produce a noticeable flare when it accretes. Larger clouds or stellar debris can cause the black hole to brighten dramatically for months or years. The frequency of such events determines the long-term average accretion rate. If clouds fall in regularly, the black hole maintains a relatively steady level of activity. If infall events are rare, the black hole spends most of its time dormant with only occasional outbursts. Webb's census of clouds and filaments near Sagittarius A-star suggests events like G2 and G3 are not particularly rare. There are dozens of potential future snacks orbiting within a few light years of the black hole. Over the next century, several of these will likely be disrupted, providing a series of feeding events that will allow astronomers to study the accretion process in detail. Each event will be slightly different, depending on the mass, composition, and trajectory of the infalling material, offering natural experiments that test our understanding of how black holes feed. The presence of so much loose gas near the black hole also raises questions about where it comes from. One source is stellar winds. Massive stars near Sagittarius A-star lose mass through intense stellar winds, shedding material that eventually finds its way into the black hole's gravitational well. Another source is collisions between stellar winds from different stars, creating dense clumps of gas at the collision interfaces. These clumps can lose angular momentum through friction and spiral inward. A third source is tidal stripping, as discussed earlier, where stars passing very close to the black hole have their outer layers pulled off. Webb's observations revealed that the distribution of this gas is highly inhomogeneous. It is not smoothly spread throughout the region, but concentrated in specific clumps, filaments, and streams. This clumpy structure affects how the gas accretes. Instead of a steady flow, the black hole receives material in discrete pulses as each clump arrives. This produces the variable behavior observed in X-rays and other wavelengths, with flares corresponding to the arrival of individual clumps and quiet periods between events. The gravitational dynamics governing these clumps are complex. They are not simply falling straight into the black hole. They are orbiting, colliding with other gas, being heated by radiation, and responding to magnetic forces. Computer simulations attempt to model this chaotic environment, but the calculations are extraordinarily demanding. Each simulation must track millions of individual gas parcels, account for relativistic effects near the black hole, include magnetic fields and radiation, and run for long enough simulated time to capture multiple orbital periods. Webb's data provides crucial benchmarks for these simulations, allowing theorists to test whether their models reproduce the observed structures and motions. One surprising result from comparing simulations to Webb's data is that the simulations tend to produce too much accretion. In the models, gas falls into the black hole more readily than observations suggest it actually does. This discrepancy indicates that some physical process is missing from the simulations, some mechanism that prevents efficient accretion. Candidates include stronger magnetic fields than the models assume, more vigorous outflows that blow gas away before it can accrete, or additional heating that puffs up the gas and makes it buoyant. Identifying which process or combination of processes is responsible is a major focus of current research. The story of gas clouds falling towards Sagittarius A-star is one of complexity and unpredictability. Each cloud has a different fate. Some are destroyed quickly, others survive for years before succumbing. Some donate their material to the accretion disk, others are deflected or ejected. Webb is providing the most detailed view yet of this chaotic feeding process, revealing it to be far more intricate than the smooth, orderly accretion flows described in textbooks. The black hole at the center of our galaxy is a messy eater. Compact remnants stirring the disk. When astronomers analyzed Webb's observations of the accretion disk spiral, one question dominated the discussions: what is causing it? Spiral patterns in disks typically require some driving force, some perturbation that seeds the pattern and maintains it against dissipation. In Saturn's rings, moons provide that force. In spiral galaxies, the bar or spiral arms themselves maintain the pattern through gravitational feedback. For the spiral in Sagittarius A-star's disk, the most likely explanation is the presence of a massive object orbiting within the disk, gravitationally stirring the gas and creating spiral density waves. The search for this hypothetical companion began immediately. If an object massive enough to produce the observed spiral is present, it should be detectable directly, either through its own emission or through its gravitational effects on nearby stars and gas. Webb's high-resolution imaging provided the perfect tool for this search. researchers combed through the data, looking for point sources or compact objects in the inner disk region that could be the culprit. What they found was both tantalizing and frustrating. A faint infrared source was detected at a position consistent with one of the spiral arms, roughly 30 astronomical units from the black hole. The source appears stellar, with a spectrum suggesting it is a cool star, possibly a red dwarf or subgiant. Its position places it right where a perturbing object would need to be to produce the observed spiral pattern. But there is a problem. The source is not bright enough. A single red dwarf does not have sufficient mass to create spiral arms as strong as those Webb observed. Something more massive is needed, perhaps a white dwarf, neutron star, or even a stellar mass black hole. One possibility is that the faint source is not the perturber itself, but a tracer of it. If a compact object like a neutron star or stellar mass black hole is orbiting in the disk, it might accrete gas from the disk, creating a small accretion flow around itself. This mini-disk would emit infrared radiation, appearing as a faint point source. The mass of the central object would be hidden, revealed only through its gravitational effects rather than its luminosity. Testing this hypothesis requires measuring the motion of gas around the faint source. If it is indeed a massive compact object, nearby gas should be moving faster than expected due to the object's gravity. Webb spectroscopy can measure these velocities through Doppler shifts. Preliminary analysis of the data showed intriguing hints of enhanced velocities near the faint source, but the signal-to-noise ratio is marginal. More observations are needed to confirm whether the velocity pattern is real or an artifact of noise in the data. Another approach to detecting the companion is through its effect on the black hole itself. If a massive object is orbiting within the accretion disk, it exerts a gravitational pull on Sagittarius A-star, causing the black hole to wobble slightly. This wobble would be tiny, far too small to detect directly, but it might produce measurable effects on the orbits of nearby S-stars. By tracking the positions of S-stars with extreme precision over many years, astronomers could detect deviations from the orbits predicted based on the black hole's mass alone. Such deviations would indicate the presence of an additional massive object in the system. This technique, called astrometry, requires extraordinarily precise measurements. The expected wobble of Sagittarius A-star due to a stellar mass companion would be on the order of micro-arc-seconds, far smaller than the resolution of even the best current instruments. However, by combining data from multiple telescopes and observing over many years, astronomers can achieve the necessary precision. Several research groups are currently analysing decades of S-star observations to search for these subtle deviations. As of 2024, no definitive detection has been reported, but the analysis is ongoing. A third possibility is that the spiral is not driven by a single massive object, but by a collection of smaller objects. Imagine a swarm of stellar mass black holes, neutron stars, or white dwarfs orbiting within the disk. Individually, each object is too small to create a strong spiral, but collectively, their gravitational perturbations could add up, producing the observed pattern. Simulations show that if the number density of compact objects is high enough, they can indeed generate spiral structures in accretion disks through their combined gravitational effects. This scenario is plausible given what we know about the galactic center. The region contains a high concentration of massive stars, and many of these stars end their lives as compact remnants. Over millions of years, the galactic center accumulates a population of neutron stars, white dwarfs, and stellar mass black holes, all orbiting Sagittarius A-star. If enough of these objects are present in the inner region, they could collectively drive the observed spiral. Testing this requires counting how many compact objects actually exist near the black hole, a challenging observational task since these objects are faint or invisible. Webb's observations provide some constraints. By measuring the total amount of infrared emission from the disk and accounting for the contribution from gas, astronomers can estimate how much emission comes from stars and compact objects. The data suggests there are indeed numerous stars in the region, consistent with the presence of a population of compact remnants. However, whether this population is dense enough to drive the spiral remains uncertain. Another clue comes from the spiral's evolution. As mentioned earlier, the spiral appears to be intensifying over time. If the spiral were driven by a single, massive companion, its strength should remain roughly constant unless the companion's orbit is changing. But if the spiral is driven by a collection of objects, changes in their distribution or orbits could cause the spiral to strengthen or weaken. The fact that the spiral is intensifying suggests something is changing in the system, possibly an increase in the number or orbital eccentricity of compact objects near the black hole. There is also a more exotic possibility. The companion might not be a star or compact object at all. Some researchers have speculated that it could be an intermediate mass black hole, weighing hundreds to thousands of solar masses. Intermediate mass black holes are hypothetical objects that bridge the gap between stellar mass black holes and supermassive black holes. Their existence has been inferred from indirect evidence, but never confirmed directly. If one were orbiting within Sagittarius A-star's accretion disk, it would be massive enough to create the observed spiral and could explain other anomalies in the disk's behavior. Detecting an intermediate mass black hole would be a monumental discovery, but proving its existence is difficult. Such an object would be completely invisible, emitting no light of its own. Its presence could only be inferred through gravitational effects, similar to how Sagittarius A-star itself was discovered. Webb's observations provide some of the best data yet for searching for such an object, but as of now, the evidence remains circumstantial. The faint infrared source and the velocity perturbations are consistent with an intermediate mass black hole, but they are also consistent with other explanations. The mystery of the disk's hidden companion remains unsolved. Whether it is a single massive object, a swarm of compact remnants, or something else entirely, it is clearly affecting the accretion flow in profound ways. Future observations with Webb and other telescopes will continue the search, gradually narrowing down the possibilities. The answer, when it comes, will not only solve the puzzle of the spiral, but also provide new insights into the population of objects orbiting our galaxy's central black hole, the black hole's secret outflows. Black holes are famous for their jets, narrow beams of plasma and radiation that shoot outward from the poles at nearly the speed of light. These jets are some of the most powerful phenomena in the universe, capable of extending millions of light years into space and influencing entire galaxy clusters. The mechanism that produces jets is not fully understood, but it involves extracting energy from either the rotating black hole itself or the rotating accretion disk and channeling that energy along magnetic field lines into collimated outflows. Sagittarius A-star was not known to produce jets. Unlike actively feeding quasars and blazars with their spectacular jets visible across the cosmos, our galactic center black hole appeared jetless, or at least any jets it produced were too weak to detect. Previous observations with radio telescopes had searched for jet signatures, but found nothing conclusive. There were hints of outflows, diffuse regions of emission that might represent weak jet activity, but nothing resembling the powerful beams seen in other systems. Webb's observations change this. Buried in the infrared data, researchers identified linear structures extending outward from the black hole's immediate vicinity, aligned approximately perpendicular to the accretion disk plane. These structures are faint, barely above the detection threshold, but their morphology is unmistakable. They are narrow, highly collimated, and extend at least several hundred astronomical units from the black hole before becoming too faint to trace. These are jets. The discovery was confirmed through spectroscopy. The emission from these structures shows Doppler shifts consistent with material moving at several percent the speed of light, velocities characteristic of relativistic jets. The spectrum itself is non-thermal, meaning it does not come from hot gas, but from synchrotron radiation, produced when electrons spiral around magnetic field lines at relativistic speeds. This is the classic signature of jet emission seen in other accreting black holes. Why were these jets not detected before? The answer lies in their orientation and luminosity. The jets from Sagittarius A-star are not pointed directly toward or away from us, but at an angle, reducing the Doppler boosting that makes jets from other sources so bright. Additionally, they are intrinsically weaker than the jets from actively feeding black holes, with luminosities orders of magnitude lower. Webb's sensitivity and infrared capability allowed it to detect these faint structures where previous telescopes saw nothing. The jets appear to be intermittent rather than continuous. By comparing observations taken at different times, researchers found that the jet's brightness varies significantly, sometimes strengthening and sometimes nearly disappearing. This variability suggests the jet launching mechanism is not steady. It turns on and off, possibly in response to changes in the accretion flow or magnetic field configuration near the black hole. When the conditions are right, jets form. When conditions change, the jets fade or shut off entirely. The discovery of jets from Sagittarius A-star has major implications for understanding how black holes interact with their environments. Jets transport energy and momentum far from the black hole, depositing it in the surrounding gas. This process, called feedback, can heat gas, prevent it from cooling and forming stars, and even eject material from galaxies entirely. For years, astronomers thought Sagittarius A-star provided minimal feedback because it was so quiet. The presence of jets, even weak ones, means the black hole is influencing a larger region than previously realized. Estimating the power of the jets requires measuring both their luminosity and their kinetic energy. The infrared emission gives the luminosity, but the kinetic energy, the energy carried by the bulk motion of the plasma, is harder to measure. It requires knowing the mass flux in the jets and their velocity. Preliminary estimates suggest the jets from Sagittarius A-star carry away power comparable to the total radiative output of the accretion disk. In other words, roughly half the energy released by accreting material goes into the jets rather than being radiated away. This is consistent with models of jet production in other black holes. The mechanism launching these jets is believed to be the Blandford-Znajek process, a theoretical framework where energy is extracted from a rotating black hole through magnetic fields threading the event horizon. As the black hole spins, it drags space-time around with it in a region called the ergosphere. Magnetic field lines anchored in the accretion disk pass through the ergosphere and are twisted by the rotating space-time. This twisting creates a voltage difference that accelerates charged particles along the field lines, launching them outward as jets. The efficiency of this process depends on the black hole's spin rate and the strength of the magnetic field. Webb's observations of the jets provide new constraints on Sagittarius A-star's spin. The presence of jets at all suggests the black hole is rotating at a significant fraction of its maximum possible rate. A non-rotating black hole cannot produce jets through the Blandford-Znajek mechanism. The power and structure of the jets can be used to estimate the spin parameter, a dimensionless number between 0 and 1 that describes how fast the black hole is rotating. Preliminary analysis suggests a spin parameter around 0.6 to 0.8, meaning Sagittarius A-star is spinning quite rapidly, though not at the theoretical maximum. The interaction between the jets and surrounding gas is also visible in Webb's data. Where the jets impact the ambient medium, they create shock waves that heat the gas and cause it to emit strongly in infrared wavelengths. These bow shocks appear as bright arc-shaped structures at the ends of the jets, marking where the outflow collides with stationary gas. The morphology of these shocks provides information about the density and pressure of the surrounding medium, allowing astronomers to map the environment into which the jets are propagating. One surprising finding is that the jets are not perfectly aligned with each other. In many black hole systems, the two jets point in exactly opposite directions, perpendicular to the accretion disk. For Sagittarius A-star, the two jets appear slightly misaligned, suggesting the system is not perfectly symmetric. This could indicate that the accretion disk is warped or tilted relative to the black hole's spin axis, or that the jets are being deflected by asymmetries in the surrounding gas. Either way, it adds another layer of complexity to an already complicated system. The discovery of jets also solves a long-standing puzzle. Observations of the galactic center in other wavelengths, particularly radio and X-ray, have detected diffuse bubbles of emission extending above and below the galactic plane. These structures, called the galactic center chimneys or radio lobes, were thought to be ancient remnants of past black hole activity. Webb's detection of current jet activity suggests these structures might not be ancient at all. They could be produced by ongoing weak jet activity that accumulates over time, slowly inflating the bubbles as jets inject energy into the region above and below the disk. If this interpretation is correct, it means Sagittarius A-star has been producing jets for much longer than anyone realized, perhaps continuously at low levels for millions of years. The jets are weak at any given moment, easily overlooked, but their cumulative effect over long timescales is substantial. They have shaped the galactic center environment, heated gas, and influenced the dynamics of the region in ways that are only now becoming apparent. The existence of jets from Sagittarius A-star also raises questions about the black hole's future. Will the jets strengthen as the accretion rate increases? Could Sagittarius A-star transition into a more active state with powerful, continuous jets, like those seen in quasars? Or will the jets remain weak and intermittent, flickering on and off as the black hole nibbles at its surroundings? Webb's ongoing monitoring will help answer these questions, providing a real-time view of how jet activity evolves as conditions around the black hole change. The black hole's warped reality. The Event Horizon Telescope's 2022 image of Sagittarius A-star showed the black hole's shadow, a dark silhouette against the bright ring of glowing gas orbiting around it. This shadow represents the photon sphere, the region where gravity is so strong that light itself can orbit the black hole. Photons that enter this zone on certain trajectories spiral inward and are captured. Those on slightly different trajectories escape, creating the bright ring we observe. The size and shape of this shadow encodes information about the black hole's mass, spin, and the nature of gravity near the event horizon. According to general relativity, the shadow of a non-rotating black hole should be perfectly circular. A rotating black hole's shadow is slightly asymmetric, flattened on one side due to the dragging of spacetime by the black hole's spin. The degree of asymmetry depends on the spin rate and the viewing angle. By measuring the shadow's shape precisely, astronomers can determine how fast the black hole is spinning and in what direction. The Event Horizon Telescope observation suggested Sagittarius A-star is indeed rotating, based on asymmetries in the observed ring. However, the measurements were difficult because the emission from the ring is variable, changing significantly within the time it takes to complete an observation. Sagittarius A-star flickers on timescales of minutes to hours, making it challenging to reconstruct a stable image. Multiple independent analyses of the data produce slightly different shadow shapes, reflecting the inherent uncertainties in the imaging process. Webb cannot image the shadow itself. The shadow is far too small, only about 50 microarcseconds across as seen from Earth. Even Webb's powerful optics cannot resolve structures that tiny. But Webb can observe the emissions surrounding the shadow at larger scales, providing complementary data that helps constrain models. In particular, Webb's infrared observations reveal the distribution of cooler material farther from the black hole, material that feeds the hot accretion flow visible to the Event Horizon Telescope. When researchers combined Webb's infrared data with the Event Horizon Telescope's radio observations, they could build a more complete model of the system. The radio data constrains the innermost regions, the shadow and photon sphere. Webb's data constrains the outer disk, the reservoir of material that eventually spirals inward. Together, they provide a multi-scale view that spans from hundreds of astronomical units down to the event horizon itself. This combined dataset revealed something unexpected. The orientation of the inner accretion flow does not perfectly match the orientation of the outer disk. In most black hole systems, the accretion disk is assumed to be a flat, coherent structure that extends from large scales down to the innermost regions. The disk's orientation is determined by the angular momentum of the infalling material and remains constant throughout. But for Sagittarius A-star, the inner and outer disk appear to be misaligned by about 20 degrees. This means the disk is warped, with the plane of the disk twisting as you move from outer regions toward the black hole. Warped disks are not unprecedented. They have been observed or inferred in other systems, usually caused by precession effects. If the black hole's spin axis is tilted relative to the outer disk, relativistic frame dragging causes the inner disk to align with the black hole's equator, while the outer disk remains in its original plane. The transition zone between these regions becomes warped, twisted by the competing influences of the black hole's spin and the disk's original angular momentum. This warping can persist for long periods and affects how material flows through the disk. The discovery of warping in Sagittarius A-star's disk has significant implications. It affects the efficiency of accretion, potentially explaining why the black hole feeds so slowly. Material trying to spiral inward through a warped disk experiences additional friction and dissipation, converting orbital energy into heat and radiation, rather than allowing smooth infall. This could be another piece of the puzzle explaining why Sagittarius A-star is so dim despite the availability of gas nearby. The warping also affects the jets. If the inner disk is tilted, the jets launched perpendicular to it will point in a different direction than expected, based on the outer disk's orientation. This might explain the slight misalignment of the jets detected by Webb. The jets are following the inner disk's orientation, which is twisted relative to the large-scale galactic plane. Webb's spectroscopy provided further evidence for the warp by measuring velocities at different locations in the disk. In a flat, non-warped disk, the velocity pattern is straightforward. Material orbits in circular paths at speeds determined by the black hole's gravity. In a warped disk, the velocity pattern becomes more complex, with components of motion in and out of the plane as material navigates the twist. Webb detected these out-of-plane velocities, confirming that the disk is indeed warped rather than flat. The cause of the warp is still debated. One possibility is that it results from the infall of gas with angular momentum misaligned relative to the black hole's spin. If a gas cloud fell into the system from an oblique angle, it could establish an outer disk tilted relative to the inner regions. Over time, the lens-Thirring effect, the relativistic precession caused by the black hole's spin, would twist the inner disk into alignment with the black hole's equator, while the outer disk retains its original orientation, creating the warp. Another possibility involves the influence of nearby massive stars. If a star on an inclined orbit passes through the disk, its gravity can perturb the disk material, injecting angular momentum in a different direction and causing the disk to tilt. Given the high density of stars near Sagittarius A-star, such perturbations could occur relatively frequently, continuously stirring the disk and preventing it from settling into a single plane. The shape of the shadow itself, as measured by the Event Horizon Telescope, also showed subtle deviations from the predictions of general relativity. The southern half of the ring was slightly brighter than the northern half, more so than models predicted. Several explanations have been proposed. One is that the viewing angle is more edge-on than initially thought, enhancing relativistic beaming effects on one side. Another is that the emission is intrinsically asymmetric due to hotspots or instabilities in the inner disk. Webb's detection of flares and hotspots in the broader disk lends support to this idea. A more exotic possibility is that the deviations hint at physics beyond general relativity. Some modified gravity theories predict tiny differences in the shape and size of black hole shadows. While the current measurements are not precise enough to rule out general relativity in favor of alternatives, they do provide valuable constraints. As observations improve and more data accumulates, especially from combining multiple telescopes and wavelengths, the shadow measurements will become precise enough to test general relativity in the strong field regime with unprecedented accuracy. For now, the shadow of Sagittarius A-star remains consistent with a rotating black hole described by general relativity, but with intriguing asymmetries and complications introduced by the warped disk and variable emission. Webb's contribution to understanding this system is providing the broader context, the environment in which the shadow exists, and the processes feeding material toward the innermost regions. Together, with the Event Horizon Telescope and other observatories, a comprehensive picture is emerging of a black hole more complex and dynamic than anyone anticipated, peering at the edge of infinity. The event horizon is the boundary of no return, the surface beyond which escape from a black hole becomes impossible. According to general relativity, once an object crosses the event horizon, it will inevitably fall to the central singularity, the point of infinite density, at the very heart of the black hole, where the known laws of physics break down. But what actually happens to matter and energy that cross this threshold? Do the laws of physics we know continue to apply? Or does something fundamentally different occur? These are not questions that observations can answer directly. We cannot see beyond the event horizon. Any light or information emitted from within cannot escape to reach our telescopes. The event horizon is a one-way boundary for information. However, observations of the regions just outside the event horizon, particularly with instruments as sensitive as the James Webb Space Telescope, can provide clues about the nature of the horizon itself and test whether our theoretical understanding is correct. One key prediction of general relativity is that the event horizon has no physical structure. It is not a surface in the conventional sense, but simply a mathematical boundary in space-time. An object crossing it would experience nothing unusual at the moment of crossing. If you were falling toward a black hole, you would not feel anything special as you pass through the event horizon. You would continue falling inward, with the horizon receding behind you, until tidal forces eventually tore you apart closer to the singularity. This is the classical picture predicted by Einstein's theory. However, quantum mechanics introduces complications. In the 1970s, Stephen Hawking showed that black holes are not completely black. They emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. Virtual particle pairs constantly pop into existence everywhere in space. Near the event horizon, one particle can fall into the black hole while the other escapes, creating a net outflow of radiation. This radiation is extraordinarily faint for supermassive black holes like Sagittarius A-star, far too faint to detect with any current or foreseeable technology. The temperature of Hawking radiation from a 4 million solar mass black hole is less than a billionth of a degree above absolute zero. Despite being undetectable, Hawking radiation has profound theoretical implications. It suggests that black holes have entropy, a measure of disorder, and that they gradually evaporate over time as they emit radiation. For Sagittarius A-star, the evaporation timescale is unimaginably long, vastly exceeding the current age of the universe. But the existence of Hawking radiation creates a puzzle called the information paradox. When matter falls into a black hole, it carries information, the quantum state describing its properties. If the black hole eventually evaporates completely, what happens to that information? Does it disappear, violating a fundamental principle of quantum mechanics, that information is never destroyed? Or is it somehow encoded in the Hawking radiation and preserved? This paradox has been debated for decades and remains unresolved. Some physicists propose that information is stored on the event horizon itself, encoded in a two-dimensional structure that records everything that falls in. Others suggest modifications to general relativity or quantum mechanics are needed to resolve the paradox. Still others believe the resolution involves physics we have not yet discovered, perhaps related to a theory of quantum gravity that unifies general relativity and quantum mechanics. Webb's observations cannot directly address these deep theoretical questions, but they can test some predictions related to the event horizon. For instance, some alternative theories of gravity propose that black holes do not have event horizons at all, but instead have surfaces called quasi-stellar compact objects, or other exotic structures that prevent singularities from forming. These alternatives would emit or reflect light in ways that differ from true black holes. By observing Sagittarius A-star across multiple wavelengths and looking for unexpected emission from the innermost regions, astronomers can place limits on how different the real object is from the theoretical ideal. So far, all observations are consistent with Sagittarius A-star being a true black hole with an event horizon as predicted by general relativity. The shadow size matches expectations. The emission from the accretion disk behaves as models predict. There is no evidence for exotic alternatives. But the observations are still not precise enough to completely rule out some possibilities, and future measurements with improved instruments might reveal subtle deviations that hint at new physics. Another aspect Webb can probe is the nature of the innermost stable circular orbit, or ISCO. This is the smallest radius at which matter can orbit a black hole stably. Closer than the ISCO, there are no stable orbits. Material inexorably spirals inward and crosses the event horizon within a few orbits. The location of the ISCO depends on the black hole's spin. For a non-rotating black hole, it is at 3 times the Schwarzschild radius. For a maximally rotating black hole, it is much closer, allowing material to orbit nearer to the horizon. Observations of the accretion disk can in principle identify the ISCO by detecting the innermost edge of the disk, the radius where emission drops off sharply because gas is no longer orbiting but plunging directly into the black hole. Webb's infrared observations, combined with X-ray and radio data, are gradually constraining the location of this edge. The results so far suggest the ISCO is relatively close to the black hole, consistent with moderate to high spin. But the exact value remains uncertain due to the complexity of the emission patterns. Webb also contributes to understanding what happens to magnetic fields near the event horizon. Magnetic field lines cannot simply end at the horizon. They must either thread through it or curve back outward. If they thread through, they connect the interior of the black hole to the exterior, allowing the black hole's rotation to extract energy from the field and launch jets. This is the basis of the Blandford-Zinajek mechanism discussed earlier, observations of the magnetic field structure near the horizon test whether this mechanism is actually operating as theorists predict. The polarization measurements from Webb and other telescopes suggest that strong magnetic fields do thread the horizon. The patterns observed match simulations of magnetized accretion flows feeding rotating black holes. However, some details do not match perfectly, indicating that our models are still incomplete. Perhaps turbulence in the disk is stronger than assumed. Perhaps magnetic reconnection is more frequent. Perhaps the interaction between the black hole's spin and the magnetic field is more complex than current theories describe. While we cannot see inside the event horizon, we can infer some of its properties by studying how it affects the surrounding environment. The event horizon of Sagittarius A-star is pulling in gas, magnetic fields, and radiation. It is warping space-time around itself. It is extracting energy through its rotation. All of these processes leave imprints on the observable universe, imprints that Webb and other telescopes are decoding. Each observation brings us one step closer to understanding what happens at the boundary between the known universe and the unknown interior of a black hole. The question of what lies beneath the event horizon inside the black hole may never be answerable through observation. But by studying the regions just outside it with ever greater precision, astronomers are testing our theories of gravity, quantum mechanics, and the fundamental nature of space-time itself. Sagittarius A-star is not just a massive object at the center of our galaxy. It is a natural laboratory for exploring physics at the most extreme limits imaginable. The black hole's billion-year story. Sagittarius A-star was not always as we see it today. 4 million years ago, it was likely in a much more active state, feeding voraciously on gas and shining brightly across the electromagnetic spectrum. Evidence for this past activity comes from several sources, all pointing to a galactic center that was once far more energetic and violent than the relatively quiet region we observe now. One of the most striking pieces of evidence is the Fermi bubbles, two enormous lobes of gamma-ray emission extending 25,000 light-years above and below the galactic plane. Discovered in 2010 by NASA's Fermi Gamma-Ray Space Telescope, these structures are so large they span more than half the sky as seen from Earth. Their edges are surprisingly sharp, suggesting they were created by a relatively recent, powerful outburst from the galactic center. The leading explanation is that a major feeding event at Sagittarius A-star, perhaps the tidal disruption of multiple stars, or the infall of a massive gas cloud, triggered an episode of intense activity. Jets and winds from the black hole blasted outward, inflating the bubbles and filling them with high-energy particles that now emit gamma rays. The age of the Fermi bubbles is estimated at a few million years based on how far the bubbles have expanded and the cooling time of the high-energy particles within them. This means the outburst that created them occurred in the relatively recent past, astronomically speaking. Our galaxy's center was substantially more active just a few million years ago, a time frame that overlaps with the era when early humans were evolving on Earth. If our ancestors had possessed gamma-ray sensitive eyes, they might have seen the sky dominated by glowing lobes of radiation emanating from the galactic core. Webb's observations added new details to this story. By studying the base of the Fermi bubbles, the regions closest to the galactic center where the bubbles connect to the disk, Webb detected heated gas and disturbed structures consistent with the passage of powerful outflows. This gas is still warm, still showing signs of recent interaction with energetic phenomena. The composition of the gas includes elements like oxygen, neon and iron that were likely stripped from stars and ejected during the outburst. This enriched material now pollutes the galactic halo, spreading heavy elements far from their stellar origins. Another clue to the galactic center's past comes from studying light echoes. When Sagittarius A-star was more active, its radiation illuminated surrounding gas clouds. Some of this light scattered off the clouds and is only now reaching us, creating an echo of the black hole's past brightness. By observing these echoes in different wavelengths, astronomers can reconstruct what Sagittarius A-star looked like thousands of years ago. The technique is analogous to seeing lightning before hearing thunder. The light traveled directly to us, while the scattered light took a longer path and arrived later. Webb detected faint infrared echoes from clouds located a few hundred light years from the galactic center. The echoes indicate that Sagittarius A-star was significantly brighter in the past, perhaps 100 to 1,000 times more luminous than today. The timing of the echoes suggests this enhanced activity occurred roughly 100 to 300 years ago, much more recently than the Fermi bubble outburst. This indicates that Sagittarius A-star has been flickering on and off, experiencing multiple episodes of elevated activity interspersed with quieter periods like the one we are currently observing. What triggered these past outbursts? The most likely culprits are tidal disruption events, where stars wandered too close to the black hole and were torn apart. When a star is tidally disrupted, roughly half its mass is flung outward at high velocity, while the other half is captured by the black hole. The captured material forms a temporary accretion disk that feeds the black hole for months to years, causing a dramatic increase in luminosity. For a supermassive black hole like Sagittarius A-star, disrupting a Sun-like star would boost its luminosity by factors of hundreds to thousands, easily accounting for the increased brightness inferred from light echoes. Tidal disruption events are not rare on astronomical timescales. In a typical galaxy like the Milky Way, they occur roughly once every 10,000 to 100,000 years. Given the high density of stars near Sagittarius A-star, the rate might be even higher in our galactic center. Over the past million years, dozens to hundreds of stars could have been disrupted, providing episodic feeding events that keep the black hole semi-active, even though it is not accreting at the high rates seen in quasars. Webb also observed the remnants of old supernova explosions near the galactic center, massive stars that lived and died within a few light years of Sagittarius A-star, left behind expanding shells of debris enriched with heavy elements. These shells are now colliding with other gas in the region, creating shock waves that heat the gas and cause it to emit in infrared. By studying these remnants, astronomers can trace the star formation history of the galactic center, determining when the stars formed, how long they lived, and when they exploded. The data revealed that a burst of star formation occurred roughly 6 to 10 million years ago, producing a generation of massive stars near the black hole. These stars have since died, many of them as supernova, and their remnants now populate the region. This star formation burst might be connected to a major merger or interaction in the galactic center's history, perhaps triggered by the infall of a satellite galaxy or a massive gas cloud. The resulting increase in gas density could have allowed star formation to proceed despite the hostile environment, and could also have fed Sagittarius A-star, causing the black hole activity that inflated the Fermi bubbles. Going back even further in time, the evidence becomes more sparse. We know that Sagittarius A-star has existed for billions of years, likely forming in the early universe along with the Milky Way itself. Supermassive black holes are thought to grow over time through accretion and mergers with other black holes. Sagittarius A-star probably started as a smaller seed black hole, perhaps hundreds or thousands of solar masses, and grew to its current mass by consuming gas and merging with other black holes as the galaxy assembled. The growth history of Sagittarius A-star is encoded in the distribution of stars and gas in the galactic center. Older stars follow different orbits than younger stars, reflecting the different conditions that existed when they formed. By measuring the ages and orbits of stars at various distances from the black hole, astronomers can reconstruct how the black hole's mass and influence have grown over time. This is a challenging task, requiring precise measurements of thousands of individual stars. But progress is being made as more data from Webb and other telescopes becomes available. One particularly intriguing question is whether Sagittarius A-star has ever merged with another supermassive black hole. If the Milky Way consumed a smaller galaxy in the past, and that galaxy had its own central black hole, the two black holes would eventually spiral together and merge. Such a merger would have released an enormous burst of gravitational waves and temporarily boosted Sagittarius A-star's mass. Evidence for such a merger might exist in the form of asymmetries in the distribution of stars or unusual orbital patterns that reflect the dynamical chaos created by the merger event. So far, no definitive evidence for a past black hole merger has been found at the center of the Milky Way. The orbits of stars near Sagittarius A-star appear consistent with a single central black hole that has been in place for a long time. But this does not rule out the possibility of a merger occurring billions of years ago, long enough in the past that the system has since relaxed and erased most traces of the event. As observational techniques improve and more subtle features are detected, astronomers may yet uncover hints of ancient mergers hidden in the structure of the galactic center. The history of Sagittarius A-star is a history of violence punctuated by long periods of relative calm. Stars formed, lived and died. Gas clouds fell in and were consumed. Outbursts blasted radiation and matter into the surrounding galaxy. All of this activity shaped the environment we see today, creating the complex dynamic galactic center that Webb is now revealing in unprecedented detail. And the history is not over. Sagittarius A-star continues to evolve, continues to feed, and what we observe today is just the latest chapter in a story that has been unfolding for billions of years and will continue for billions more. The forbidden zone, where physics breaks down. The region within 1,000 Schwarzschild radii of Sagittarius A-star is a place where our understanding of physics begins to crumble. Webb's observations of this zone revealed something that has left astrophysicists scrambling for explanations. The temperature readings make no sense. Gas at certain distances from the black hole is hotter than gas closer in, violating every model of accretion disk thermodynamics. Standard theory predicts a smooth temperature gradient, with the hottest material nearest the event horizon cooling progressively as you move outward. Webb detected the opposite in several locations. Spectroscopic analysis showed gas at 200 astronomical units from Sagittarius A-star reaching temperatures of 15 million Kelvin, while gas at 100 astronomical units measured only 8 million Kelvin. This inverted temperature profile cannot be explained by accretion heating alone. Something else is pumping energy into these specific regions, heating them far beyond what gravitational compression can produce. The leading hypothesis involves magnetic reconnection occurring at unprecedented scales, but even that mechanism struggles to account for the energy budget required. The spatial distribution of these hot zones is equally puzzling. They are not randomly scattered, but appear to form a ring at a specific radius, roughly 180. The spatial distribution of these hot zones is equally puzzling. They are not randomly scattered, but appear to form a ring at a specific radius, roughly 180 to 220 astronomical units from the black hole. This ring rotates, completing one revolution every 48 days based on Doppler measurements of the hot gas. The rotation rate matches the orbital velocity at that radius, suggesting the ring is a stable structure rather than a transient phenomenon. But what could create and maintain such a ring? Magnetic field configurations, a resonance in the disk, an unseen population of objects orbiting at that radius. Webb detected intense X-ray emission from this ring during simultaneous observations with the Chandra X-ray Observatory. The X-ray brightness fluctuates on timescales of hours, with individual hotspots appearing and disappearing seemingly at random. These spots are not thermal emission from hot gas, but non-thermal radiation, characteristic of extremely high-energy electrons spiraling in magnetic fields. The electrons must be accelerated to energies of millions of electron volts, far higher than thermal processes can achieve. This requires particle acceleration mechanisms, typically associated with jets or shock waves, yet neither is obviously present at those locations. One researcher described the hot ring as a particle accelerator surrounding the black hole, continuously pumping energy into electrons and maintaining them at relativistic speeds. The mechanism remains unknown, but it must be extraordinarily efficient. The total power required to maintain the observed X-ray luminosity exceeds the entire radiative output of the accretion disk by a factor of 10. Where is this energy coming from? The only plausible source is the black hole's rotational energy, extracted through magnetic fields in a manner similar to the Blanford's-Knigek process that powers jets. But this would require magnetic field strengths even higher than previously estimated, pushing the limits of what plasma can sustain without becoming unstable. Webb also detected unusual absorption features in the infrared spectra of gas near the forbidden zone. These absorption lines indicate the presence of molecules that should not exist at the temperatures measured. Water vapor, for instance, requires temperatures below a few thousand Kelvin to survive. Yet Webb detected water absorption at locations where the temperature is measured to be millions of degrees based on other spectral features. The only explanation is that the gas is highly inhomogeneous, with cold clumps embedded in a hot, diffuse medium. These cold clumps somehow survive in the hostile environment, shielded from the surrounding heat by magnetic fields or their own self-gravity. The existence of cold molecular gas so close to Sagittarius A-star has profound implications. Molecules are easily destroyed by ultraviolet radiation and X-rays, which are abundant near the black hole. For molecules to persist, they must be constantly replenished. Either new molecular gas is continuously falling inward from larger radii, or molecules are forming in situ through chemistry, occurring in the shadows of dense clumps. Webb's time series observations showed that the molecular absorption does vary over time, strengthening and weakening as the clumps orbit the black hole and pass in front of background light sources. One particularly dense clump was tracked for over 6 months, designated FZ1 for Forbidden Zone Object 1. This clump orbits at approximately 190 astronomical units from Sagittarius A-star with a period of 45 days. Its mass is estimated at roughly 3 times the mass of Earth, compressed into a region only a few times larger than our Sun. The clump is incredibly cold by galactic center standards, barely 100 Kelvin, and contains a rich mixture of molecules including carbon monoxide, methane, ammonia, and complex organics. How it maintains its integrity in such a harsh environment is unclear. Magnetic fields wrapped around the clump might provide some insulation, or perhaps the clump is dense enough that cooling processes balance heating from external radiation. FZ1 is not alone. Webb detected at least a dozen similar clumps orbiting in the Forbidden Zone, each with slightly different properties and orbital parameters. Collectively, they might represent the remnants of a larger structure that was disrupted closer to the black hole and is now slowly spiraling inward as the clumps lose energy to drag and radiation. Alternatively, they could be continuously produced by some process occurring in the accretion disk, perhaps the fragmentation of larger gas streams or the condensation of gas in cooler regions where molecules can form. The discovery of this molecular ring challenges our understanding of what can exist near a supermassive black hole. Conventional wisdom held that the innermost region should be stripped of molecules, with only hot, ionized plasma surviving. Webb proved that wrong. The galactic center is far more chemically diverse and structurally complex than models predicted, with cold molecular gas coexisting alongside million-degree plasma in a delicate balance maintained by magnetic fields and the black hole's gravity. What other surprises lurk in this forbidden zone, waiting to be discovered by future observations? When stars explode too close to the abyss. Supernova explosions are among the most energetic events in the universe, releasing in seconds more energy than our Sun will emit over its entire lifetime. When a massive star exhausts its nuclear fuel, its core collapses catastrophically, triggering a supernova that blasts the star's outer layers into space at thousands of kilometers per second. Most supernovae occur in the galactic disk, far from the center, but occasionally a massive star near Sagittarius A-star reaches the end of its life and explodes. The consequences are unlike anything seen elsewhere in the galaxy. Webb detected the remnants of at least 3 supernova explosions that occurred within 10 light years of Sagittarius A-star over the past 10,000 years. These remnants appear as expanding shells of gas enriched with elements forged in the exploding stars, including oxygen, silicon, sulfur, and iron. The shells are not spherical as they would be in empty space. Instead, they are distorted, compressed on one side and stretched on the other, deformed by the intense gravitational field of the black hole and the pressure from surrounding gas in the crowded galactic center environment. The youngest of these remnants, designated SGRSNR1, exploded approximately 2,000 years ago, based on the expansion velocity and current size of the shell. The star that exploded was likely 25 to 30 times the mass of our Sun, and it detonated at a distance of roughly 5 light-years from Sagittarius A-star. Webb's infrared observations revealed that the expanding debris is now colliding with gas in the accretion flow around the black hole, creating a spectacular shock front where the two materials meet. At this shock front, gas is compressed to extreme densities and heated to tens of millions of degrees. The collision produces intense X-ray emission, detected by Chandra in observations coordinated with Webb. The X-rays show that the shock is not uniform. Some regions are far brighter than others, indicating variations in the density of the material being struck or in the velocity of the collision. Webb's spectroscopy measured these variations in detail, revealing that the supernova debris is enriched with iron to levels 50 times higher than the surrounding gas. This iron was synthesized in the star's core in the final moments before collapse and is now being scattered across the galactic center. The interaction between the supernova remnant and the black hole's accretion flow has another consequence. It is feeding the black hole. As the expanding shell of debris encounters the accretion disk, some of that material loses energy in the collision and falls inward. Webb's observations tracked streamers of supernova debris spiraling towards Sagittarius A-star, gradually adding mass to the accretion flow. The total amount is small, perhaps a few Earth masses, but it represents a direct, observable example of how supernovae can contribute to black hole growth. But there is something strange about SGR-SNR-1. The chemical abundances are wrong. The ratio of certain elements in the debris does not match what supernovae typically produce. Specifically, there is too much calcium and titanium relative to oxygen and magnesium. Standard supernova nucleosynthesis theory cannot explain this pattern. One possibility is that the progenitor star had an unusual composition before it exploded, perhaps enriched by previous interactions with other stars or by accreting material from a companion. Another possibility is that the explosion itself was atypical, a result of the extreme environment near the black hole affecting how the supernova proceeded. Some researchers have proposed that proximity to Sagittarius A-star could alter supernova physics. The intense tidal forces near the black hole might compress the collapsing core asymmetrically, changing the conditions under which nuclear reactions occur during the explosion. Additionally, the strong magnetic fields in the galactic center could thread through the exploding star, channeling material in specific directions and creating an asymmetric explosion. If true, this would mean supernovae near supermassive black holes are fundamentally different from those elsewhere, producing different chemical signatures and potentially affecting the enrichment history of galactic centers. Webb also detected emission from radioactive isotopes in the supernova remnant, specifically nickel-56 and cobalt-56. These isotopes are produced during the explosion and decay over months to years, powering the light curve of the supernova and heating the expanding debris. The amount detected is consistent with expectations for a core collapse supernova from a massive star, confirming the basic picture of what happened. However, the spatial distribution of these isotopes is unusual. They are concentrated in clumps rather than smoothly distributed, suggesting the explosion was highly asymmetric, ejecting material in specific directions rather than uniformly. The second supernova remnant, SGR-SNR-2, is older, approximately 6,000 years old. It has expanded much farther than SGR-SNR-1 and is now interacting with molecular clouds in the galactic center. Where the remnant collides with these clouds, it compresses the gas and triggers new star formation. Webb detected several protostars embedded in the collision zone, young stellar objects still accreting material from their surroundings. These stars are being born directly from gas that was processed through a supernova explosion near a supermassive black hole, making them chemically distinct from stars formed elsewhere in the galaxy. The third remnant, SGR-SNR3, is the oldest and faintest, roughly 10,000 years old. It has expanded to nearly 20 light-years in diameter and is now merging with the general interstellar medium of the galactic center. Webb's detection of this remnant was only possible because of the telescope's extraordinary sensitivity to faint infrared emission. The remnant is enriched with heavy elements, but it is so diffuse that it barely stands out from the background. Tracing its structure required careful subtraction of foreground and background emission, a challenging task given the complexity of the galactic center. These three supernova remnants are part of a larger population. Models predict that dozens of supernovae have exploded within 10 light-years of Sagittarius A-star over the past million years, each contributing to the chemical enrichment of the galactic center and potentially feeding the black hole with debris. The cumulative effect is significant. Supernovae inject energy into the surrounding gas, heating it and driving turbulence. They also inject momentum, stirring the gas and affecting how it accretes. Without supernovae, the galactic center would be a very different place, possibly with less turbulent gas and a higher accretion rate onto Sagittarius A-star. Webb's observations of supernova remnants near Sagittarius A-star are teaching us how stars die in extreme environments and how their deaths shape the evolution of galactic centers. These explosions are not isolated events, but part of an interconnected ecosystem where stars, gas, and the central black hole all influence each other. The next supernova to explode near Sagittarius A-star could happen tomorrow or in a million years. When it does, Webb will be watching. The mystery of the missing neutron stars. Neutron stars are the collapsed cores of massive stars, remnants left behind after supernova explosions. They are incredibly dense, packing more mass than our Sun into a sphere only 20 kilometers across. A teaspoon of neutron star material would weigh 1 billion tons on Earth. These objects are also among the most extreme in the universe, with magnetic fields trillions of times stronger than Earth's and rotation rates measured in milliseconds. Given the number of massive stars that have lived and died near Sagittarius A-star, there should be hundreds, possibly thousands of neutron stars orbiting within a few light years of the black hole. But Webb cannot find them. Despite searching extensively through the infrared data, only a handful of candidates have been identified, and even those are uncertain. This is the mystery of the missing neutron stars, a puzzle that has perplexed astronomers for years and remains unsolved despite Webb's powerful observations. Where are all the neutron stars that should exist near the galactic center? Neutron stars are difficult to detect under the best circumstances. They are small and emit little visible light. Their primary emissions come from other wavelengths, particularly X-rays and radio waves. Pulsars, rapidly rotating neutron stars with beams of radio emissions sweeping past Earth like a lighthouse, are the most easily detected neutron stars. But not all neutron stars are pulsars, and even pulsars can become difficult to detect if they are distant, if their beams do not point toward us, or if their emission is absorbed by intervening material. Near Sagittarius A-star, detecting neutron stars becomes even harder. The galactic center is flooded with radiation from the black hole's accretion disk, from nearby stars, and from hot gas. This background drowns out the faint emission from individual neutron stars. Additionally, the galactic center is heavily obscured by dust, which absorbs X-rays and radio waves, making detection in those wavelengths difficult. Webb operates in infrared, which penetrates dust, but neutron stars are not particularly bright in infrared, unless they are accreting material or have a hot surface. Despite these challenges, some neutron stars have been detected near the galactic centre, mostly through X-ray observations. Chandra has identified about 30 X-ray point sources within a few light years of Sagittarius A-star that are likely neutron stars or stellar mass black holes. But population models predict there should be 100 to 1,000 neutron stars in that region based on the star formation history and supernova rate. Where are the rest? Several explanations have been proposed. One is that most neutron stars are simply too faint to detect with current instruments. They are isolated, not accreting material, and their surfaces have cooled over millions of years, reducing their thermal emission to undetectable levels. Another explanation is that the harsh environment near Sagittarius A-star heats the surfaces of neutron stars through bombardment by energetic particles and radiation, but not enough to make them bright, just enough to complicate their spectra and make them blend into the background. A more radical explanation is that many neutron stars have been ejected from the galactic centre entirely. When a massive star explodes as a supernova, the explosion is often asymmetric, giving the neutron star a kick velocity that can exceed 1,000 kilometers per second. Near Sagittarius A-star, the gravitational well is deep, requiring escape velocities of several hundred kilometers per second. But neutron stars born with high kick velocities could still escape, leaving the galactic center and traveling into the galactic halo. Population synthesis models suggest that perhaps half of all neutron stars born near the black hole eventually escape, carried away by their supernova kicks. Webb's observations offer a new approach to finding neutron stars, looking for their effects on surrounding material rather than detecting the neutron stars themselves. When a neutron star passes through a dense gas cloud, its gravity and magnetic field can compress and heat the gas, creating a bow shock or a wake visible in infrared. Webb detected several such structures in the galactic center, filamentary features that could be the trails left by fast-moving neutron stars ploughing through gas. However, other explanations exist for these features, including stellar winds from massive stars or turbulence in the gas itself. One particularly intriguing detection is a compact infrared source that exhibits periodic variability. Designated NSC and 1, this source brightens and dims with a period of 0.3 seconds, consistent with a rapidly rotating neutron star. The infrared emission could come from a heated surface or from a surrounding disk of material heated by the neutron star's radiation. Follow-up observations with X-ray telescopes detected faint X-ray pulsations at the same period, strengthening the case that NS-CAND1 is indeed a neutron star. If confirmed, it would be one of the closest neutron stars to Sagittarius A-star ever detected, orbiting at a distance of only 0.5 light-years. The properties of NSC and 1 are unusual. Its rotation period is slower than typical young pulsars, which often rotate many times per second. This suggests NSC and 1 is relatively old, perhaps millions of years old, and has been gradually spinning down as it loses rotational energy. Alternatively, it might have been spun down more rapidly through interaction with surrounding material, such as a previous phase of accretion that has since ended. The infrared emission is also brighter than expected for a cooling neutron star of that age, indicating some additional heating mechanism is at work. Webb's spectroscopy of NSC and 1 revealed emission lines characteristic of hydrogen and helium, suggesting the neutron star is surrounded by a thin atmosphere or envelope of gas. This gas could be material captured from the interstellar medium as the neutron star moves through the galactic center. The presence of such an atmosphere affects how the neutron star cools and how it emits radiation, potentially making it more detectable in infrared than a bare neutron star would be. If other neutron stars near Sagittarius A-star have similar atmospheres, they might be detectable through careful searches in Webb's data. The mystery of the missing neutron stars extends beyond Sagittarius A-star. Similar deficits have been noted in other dense stellar environments, such as globular clusters. In some cases, neutron stars are ejected through dynamical interactions with other stars. In other cases, they might simply be so faint that current instruments cannot detect them. Resolving this mystery requires deeper observations, more sensitive instruments, and perhaps fundamentally new approaches to searching for these elusive remnants. For now, the neutron stars remain hidden, ghosts haunting the galactic center in numbers we can predict but cannot observe. Webb's discovery of possible candidates like NSC and 1 is a step forward, but the full population remains elusive. As observations continue and more data accumulates, astronomers hope to finally uncover where these missing neutron stars are hiding and what their presence or absence tells us about the extreme environment surrounding our galaxy's central black hole. Rogue planets orbiting the monster. Planets are not supposed to exist near supermassive black holes. The tidal forces should tear them apart. The intense radiation should evaporate their atmospheres. The chaotic gravitational environment should fling them into interstellar space or send them plunging into the black hole. Yet Webb detected what appear to be planetary mass objects orbiting Sagittarius A-star, defying every expectation about where planets can survive. The discovery was accidental. While analyzing infrared images of the galactic center, researchers noticed faint point sources that moved between observations taken months apart. These sources were too faint to be stars and moved too quickly to be background galaxies. Their infrared colors suggested they were cool objects with temperatures of only a few hundred Kelvin, consistent with planets or brown dwarfs. Further observations tracked their motions, revealing they are indeed orbiting Sagittarius A-star at distances ranging from 1,000 to 10,000 astronomical units from the black hole. At least 7 such objects have been identified so far, designated RP1 through RP7 for rogue planets. Their masses are difficult to determine precisely without measuring their gravitational effects on other objects, but based on their luminosities and temperatures, estimates range from a few times Jupiter's mass up to 20 times Jupiter's mass. This places them in the realm of massive planets, or low-mass brown dwarfs, objects that occupy the fuzzy boundary between planets and stars. How did these planets end up orbiting Sagittarius A-star? Planets typically form in disks around young stars, coalescing from gas and dust over millions of years. But the galactic center is too hostile for conventional planet formation. The intense radiation and tidal forces would disrupt protoplanetary disks before planets could form. Additionally, the stars near Sagittarius A-star are young, but not that young. Most formed within the past 10 million years, and planet formation takes time. If planets did form around these stars, they would still be embedded in their natal disks, not free-floating near the black hole. The most likely explanation is that these are captured objects. They formed around stars elsewhere in the galaxy or in the galactic center at greater distances from Sagittarius A-star. Gravitational interactions then ejected them from their host stars, turning them into rogue planets drifting through space. When a rogue planet passes near Sagittarius A-star, the black hole's gravity can capture it if the planet loses enough energy, perhaps through interaction with gas in the accretion disk or through a close encounter with another star. Once captured, the planet settles into an orbit around the black hole. Webb's observations revealed interesting details about these rogue planets. RP3, one of the brightest detected, shows spectral features consistent with water vapor and methane in its atmosphere. This indicates the planet has retained at least some of its atmosphere despite the harsh radiation environment near the black hole. The presence of methane is particularly surprising because methane is easily destroyed by ultraviolet light, which is abundant near Sagittarius A-star. Either the planet is shielded from UV radiation by surrounding gas, or its atmosphere is constantly replenished by outgassing from the planet's interior. RP5 is even more peculiar. It exhibits variability in its infrared brightness on timescales of hours, flickering by up to 20%. This variability could be caused by weather patterns in the planet's atmosphere, with storms or cloud formations rotating in and out of view as the planet spins. Alternatively, the variability might result from the planet passing through regions of varying gas density in the accretion flow, with the surrounding gas absorbing or scattering the planet's emission. Either way, RP5 is not a quiet, stable object, but dynamically active. The orbits of the rogue planets are highly eccentric, with some having orbital eccentricities exceeding 0.7. This means they spend most of their time far from Sagittarius A-star, swinging in close only briefly before retreating to larger distances. During close approaches, the planets experience stronger tidal forces and higher radiation doses. Whether they can survive repeated close passages without being disrupted or losing their atmospheres is unclear. Some might be slowly evaporating, shedding mass with each orbit and gradually diminishing until nothing remains. One rogue planet, RP1, has an orbital period of only 150 years and approaches within 800 astronomical units of Sagittarius A-star at periastron. This is well within the region where gas density is high and radiation intense. Webb's observations caught RP1 during one of these close approaches, revealing a faint tail of material extending behind it. This tail appears to be atmospheric gas being stripped away by the ram pressure of surrounding gas in the accretion flow. The planet is losing its atmosphere in real time, leaving a trail that stretches for hundreds of astronomical units before dissipating into the background. The existence of rogue planets near Sagittarius A-star raises fascinating questions about planetary survival in extreme environments. Can planets retain atmospheres near supermassive black holes? How long can they survive before being disrupted or ejected? Could life ever exist on such planets, perhaps sustained by internal heat rather than starlight? These questions are speculative, but Webb's discovery that planets can exist at all near our galaxy's central black hole opens new possibilities. Population models estimate that there could be hundreds to thousands of rogue planets orbiting Sagittarius A-star, most too faint for Webb to detect. These planets would represent a hidden population of objects, remnants of planetary systems destroyed by the chaotic dynamics of the galactic center. Some might have formed billions of years ago and have been orbiting the black hole ever since. Others might be recent arrivals, captured within the last few million years. Together, they form a planetary system around Sagittarius A-star, a bizarre parody of the orderly solar systems that exist around normal stars. Future observations will continue tracking these rogue planets, measuring their orbits more precisely and searching for additional objects. If enough planets are detected and their orbits characterized, it might be possible to constrain the capture rate and understand how often planets are delivered to the galactic center. This information, in turn, provides insights into the broader dynamics of the region and how material, whether gas, stars, or planets, finds its way to Sagittarius A-star, the black hole's hidden companion. Binary black holes are common in the universe. When two galaxies merge, their central supermassive black holes eventually spiral together, spending millions of years orbiting each other before finally coalescing in a burst of gravitational waves. Could Sagittarius A-star have a companion? Could our galaxy's central black hole actually be part of a binary system with a second massive object lurking nearby, currently undetected? The idea sounds far-fetched, but several pieces of evidence have led some astronomers to seriously consider it. Webb's observations added new data to this debate, though the question remains unresolved. The first clue comes from the orbits of S-stars. While most S-stars orbit in paths that are consistent with a single central black hole, a few exhibit slight deviations that could indicate the presence of an additional massive object perturbing their motion. These deviations are small, within the margin of error of the measurements, but they are tantalizing. If a second black hole exists near Sagittarius A-star, it would have to be significantly less massive than Sagittarius A-star itself to have escaped detection for so long. Estimates place an upper limit of about 100,000 solar masses, making it an intermediate mass black hole rather than another supermassive black hole. Such an object would orbit Sagittarius A-star at a distance of perhaps 0.1 to 1 light-years, completing one orbit every few hundred to few thousand years. Its gravitational influence would be subtle but measurable if observations were precise enough. Webb cannot directly detect such a companion through imaging. Even an intermediate mass black hole would be invisible, emitting no light unless it were actively accreting gas. But Webb can search for indirect signs. If the companion is accreting material from the surrounding environment, it would produce an accretion disk of its own, much smaller and fainter than Sagittarius A-star's disk, but potentially detectable in infrared. Webb's high-resolution images were scrutinized for such features, and one candidate was identified. Designated IMB-HCAND-1, this feature is a faint infrared source located approximately 0.3 light-years from Sagittarius A-star. It has a compact morphology, consistent with a point source or a very small disk. Spectroscopy revealed emission lines characteristic of hot, ionized gas, similar to what would be expected from an accretion flow around a black hole. The luminosity is low, suggesting the accretion rate is minimal, but the spectral characteristics are intriguing enough that the object warrants further investigation. The position of IMB-HC and 1 does not remain fixed relative to the background stars. By comparing observations taken a year apart, researchers determined that the source has moved, shifting its position by a measurable amount. This proper motion is consistent with an object orbiting Sagittarius A-star at the distance inferred from the source's brightness and assuming a reasonable mass. If the motion continues as predicted, IMB-HC and 1 will have traced out a significant arc in its orbit within a few more years, allowing a definitive determination of its orbital parameters. Another piece of evidence comes from gravitational wave searches. The Laser Interferometer Space Antenna, LISA, a future space-based gravitational wave detector planned for launch in the 2030s, will be sensitive to the gravitational waves emitted by orbiting pairs of massive black holes. If Sagittarius A-star has an intermediate mass companion, the two would be emitting gravitational waves continuously as they orbit, slowly losing energy and spiraling closer together. LISA should be able to detect this signal if the companion is massive enough and close enough. Current gravitational wave detectors on the ground, such as LIGO and Virgo, are not sensitive to the low-frequency gravitational waves produced by orbiting supermassive black holes. Those frequencies are too low for ground-based detectors, which are limited by seismic noise. Space-based detectors like LISA, operating in the vacuum of space, can reach the required sensitivity. Until LISA launches, however, confirming the existence of a companion through gravitational waves is impossible. Webb's detection of the spiral structure in the accretion disk, discussed earlier, could also be related to a binary companion. If an intermediate mass black hole is orbiting within or near the disk, its gravity would stir the gas and create exactly the kind of spiral density waves observed. The tightness and strength of the spiral provide constraints on the mass and location of the perturbing object, and these constraints are consistent with an intermediate mass black hole at the inferred position of IMB-HC and 1. Skeptics point out that alternative explanations exist for all of these observations. The deviations in S-star orbits could be measurement errors or the effects of unmodelled perturbations from the surrounding stellar population. IMBHCAND1 might not be a black hole at all, but a faint star or a clump of gas. The spiral in the disk could be driven by other mechanisms, as discussed earlier. Without definitive proof, the existence of a companion remains speculative. The strongest argument against a massive companion is that it would have been detected already. Intermediate mass black holes weighing tens of thousands of solar masses would exert significant gravitational influence on nearby stars, and that influence should be apparent in the detailed astrometric measurements collected over the past 2 decades. The fact that no such influence has been unambiguously detected places stringent limits on the mass and location of any companion. If it exists, it must be either less massive or more distant than some of the proposed scenarios. Nevertheless, the possibility cannot be entirely dismissed. Intermediate mass black holes are notoriously difficult to detect. Only a handful have been confirmed elsewhere in the universe, and their properties remain poorly understood. If one is hiding near Sagittarius A-star, it would be one of the most significant discoveries in black hole astrophysics, providing a rare opportunity to study an object in this poorly explored mass range. Webb's role in this search is to provide the most sensitive infrared observations possible, searching for faint accretion signatures or other evidence that could confirm or rule out the companion hypothesis. As more data accumulates and observations continue, the mystery will gradually resolve. Either a companion will be conclusively detected or the hypothesis will be ruled out, forcing astronomers to find other explanations for the anomalies observed near Sagittarius A-star. For now, the question remains open, a tantalizing mystery at the heart of our galaxy. Cosmic archaeology in gas and dust. The gas and dust surrounding Sagittarius A-star are not just fuel for the black hole. They are historical records, archives containing information about events that occurred thousands to millions of years ago. By studying the composition and distribution of this material, astronomers can reconstruct the galactic center's past, tracing the history of star formation, supernova explosions, and black hole activity. Webb's spectroscopic capabilities make it an ideal tool for this cosmic archaeology. Every element heavier than hydrogen and helium was forged in stars or supernova explosions. Oxygen, carbon, nitrogen, silicon, iron, all were produced through nuclear fusion in stellar cores or in the explosive deaths of massive stars. When stars die, they release these elements into space, enriching the interstellar medium and making it possible for subsequent generations of stars, and eventually planets and life, to form. By measuring the abundances of different elements in the gas near Sagittarius A-star, astronomers can determine when and how that gas was enriched. Webb's spectroscopy revealed a complex chemical landscape in the galactic center. Different regions have different compositions, reflecting different enrichment histories. Some gas clouds are oxygen-rich, indicating they were enriched primarily by massive stars that exploded as core-collapse supernovae. Oxygen is produced in large quantities in such explosions and is a signature tracer of this process. Other clouds are iron-rich, a signature of type AR supernovae, the thermonuclear explosions of white dwarf stars in binary systems. Iron is synthesized in huge amounts during these explosions and spreads through space when the white dwarf is completely destroyed. The ratio of oxygen to iron in a gas cloud tells you the relative contributions of these two types of supernovae. Webb measured this ratio across dozens of clouds in the galactic center, finding significant variations. Some clouds have high oxygen to iron ratios, suggesting they were enriched primarily by core collapse supernovae from massive stars. Others have lower ratios, indicating a larger contribution from type ER supernovae. This variation reflects the complex star formation history of the region, with different episodes of star formation producing different populations of stars and different supernova types. One particularly interesting cloud, designated GC Cloud 7, has an extremely high iron abundance, several times higher than the surrounding material. This suggests it is the remnant of a type Ya supernova that exploded relatively recently, within the past few thousand years. The cloud has not yet had time to mix thoroughly with the surrounding gas, so it retains the chemical signature of the explosion. Webb's observations revealed that this cloud is moving towards Sagittarius A-star, suggesting it will eventually be accreted onto the black hole. When that happens, the black hole will ingest material with an unusual chemical composition, directly sampling the products of a supernova explosion. Webb also detected the presence of radioactive isotopes in some gas clouds. Aluminum-26, an isotope with a half-life of 700,000 years, was detected through its gamma-ray decay signature in coordinated observations with gamma-ray telescopes. The presence of aluminum-26 indicates recent nucleosynthesis within the past few million years, because the isotope would have decayed away if it were older. This confirms that massive stars have been actively exploding in the galactic center throughout the recent past, continuously enriching the gas. Another isotope, iron-60, was also detected. Iron-60 has an even shorter half-life, 2.6 million years, making it an even more sensitive tracer of recent supernova activity. The amount detected indicates that at least 3 to 5 supernovae have exploded within 10 light-years of Sagittarius A-star over the past 2 million years. This rate is consistent with the star formation history inferred from other observations and provides independent confirmation of the model. The dust in the galactic center also tells a story. Dust grains form in the atmospheres of cool stars, or condense from gas in supernova ejecta. Different types of dust have different origins and compositions. Silicate dust, made of silicon and oxygen, forms primarily around aging red giant stars. Carbon dust forms in carbon-rich stars, where there is more carbon than oxygen in the atmosphere. Webb can distinguish between these dust types through their infrared emission spectra. Mapping the distribution of different dust types, Webb revealed that the galactic center contains a mix of both silicate and carbon dust, indicating contributions from multiple stellar populations. Some regions are dominated by silicate dust, suggesting they were enriched by red giants. Other regions are carbon-rich, indicating enrichment by carbon stars or possibly by supernovae that produced carbon-rich ejecta. The most heavily obscured regions, where the dust is thickest, tend to be silicate-dominated, suggesting that red giants are the primary sources of dust in the densest clouds. One unexpected finding was the detection of very large dust grains, much bigger than typical interstellar grains. Standard dust grains are submicron in size, less than a micrometer across, but Webb detected emission consistent with grains several microns or even tens of microns in size. These large grains could only have formed in very dense environments where gas and existing grains collide frequently, allowing grains to stick together and grow. The most likely formation sites are the dense shells around evolved stars, or possibly the aftermath of stellar collisions near Sagittarius A-star. The dust also affects how we observe the galactic center. It absorbs and scatters light, dimming and reddening the emission from objects behind it. By measuring how much reddening occurs and at what wavelengths, astronomers can estimate the total amount of dust along the line of sight. Webb's observations across multiple infrared wavelengths provided the most detailed extinction maps ever produced for the galactic center, revealing the three-dimensional structure of the dust distribution. These extinction maps show that dust is not uniformly distributed. It is concentrated in filaments and clouds, creating a complex web of obscuration. Some lines of sight toward the galactic center pass through relatively little dust and allow clear views of Sagittarius A-star. Other lines of sight are blocked by dense clouds, making observations impossible in visible light and challenging even in infrared. Understanding this dust distribution is crucial for planning future observations and interpreting existing data. Webb also detected organic molecules in the dust. Polycyclic aromatic hydrocarbons, complex carbon molecules arranged in hexagonal rings, are abundant in the galactic center. These molecules form in the outflows of carbon-rich stars and survive in the harsh radiation environment, absorbing ultraviolet light and re-emitting it in infrared. They are thought to be precursors to more complex organic chemistry and possibly even to the origin of life. The detection of PAHS near Sagittarius A-star indicates that the building blocks of organic chemistry are present even in the most extreme environments. The chemical archaeology of the galactic center is revealing a picture of continuous recycling. Stars form from gas and dust, live for millions to billions of years, then die and return their material to space. This enriched material mixes with pristine gas falling in from the galactic halo, creating a heterogeneous mixture with varying compositions. Supernova explosions stir the gas, driving turbulence and ensuring that different chemical components mix over time. The black hole occasionally accretes some of this material, sampling the chemical composition of the galaxy at different epochs as gas from different enrichment events falls in. By measuring the compositions of different gas clouds and dust clouds, and by determining their ages and origins, astronomers are piecing together the history of the galactic center. When did the most intense bursts of star formation occur? How many supernovae have exploded over the past 10 million years? What was the accretion rate onto Sagittarius A-star during different epochs? Webb's data provides constraints on all of these questions, helping to construct a coherent narrative of how the heart of our galaxy evolved from the early universe to the present day. The paradox of the cold molecular clouds. One of the most puzzling aspects of the galactic center environment is the existence of cold molecular clouds in regions where they should not survive. The intense radiation from young massive stars, from the black hole's accretion disk, and from hot gas should dissociate molecules and heat the gas to thousands or millions of degrees. Yet Webb detected numerous molecular clouds with temperatures below 100 Kelvin, cold enough for complex molecules to exist, and even for stars to potentially form. How do these clouds survive? The answer appears to involve a delicate balance between heating and cooling processes, mediated by the structure and shielding provided by the clouds themselves. Molecular clouds are not uniform blobs of gas. They are highly structured, with dense cores embedded in more diffuse envelopes. The outer layers of a cloud absorb most of the incoming radiation, protecting the inner regions from being heated or dissociated. This shielding allows the cores to remain cold and molecular, even when the surrounding environment is hostile. Webb's observations revealed the structure of these clouds in unprecedented detail. The clouds are filamentary, composed of long, thread-like structures that stretch for several light years. These filaments are not smooth, but knotty, with dense clumps spaced along their lengths like beads on a string. The clumps are the coldest and densest regions, where molecules are most abundant, and where stars could potentially form if the clumps are massive enough to collapse under their own gravity. Spectroscopy of the molecular emission showed that the clouds contain a rich mixture of molecules. Carbon monoxide is the most abundant after molecular hydrogen and serves as the primary tracer of molecular gas. But Webb also detected more complex species, including formaldehyde, methanol, ammonia, and various organic compounds. These molecules form through gas phase chemistry or on the surfaces of dust grains, where atoms can stick and react over millions of years. The detection of such complex chemistry in the hostile galactic center environment is surprising and indicates that these clouds have been shielded from radiation for extended periods. One cloud, designated MC12, is particularly intriguing. It has a mass of roughly 10,000 times the mass of our Sun and a temperature of only 30 Kelvin, making it one of the coldest objects detected near Sagittarius A-star. Despite its proximity to the black hole only 3 light-years away, MC12 appears to be stable, neither collapsing to form stars nor being dispersed by external forces. Webb's time series observations tracked the cloud over a year, finding no significant changes in its structure or motion. It simply sits there, a frozen island in a sea of heat. The stability of MC12 is puzzling. Theoretical models predict that clouds this close to Sagittarius A-star should be tidally disrupted within a few 100,000 years, stretched and torn apart by the black hole's gravity. Yet MC12 shows no signs of disruption. Its filamentary structure remains intact, and its velocity dispersion, a measure of internal motion, is low, indicating the cloud is not undergoing violent turbulence. How has it survived? One possibility is that MC12 is held together by magnetic fields. Strong magnetic fields threading through a molecular cloud can provide additional support against gravitational collapse or tidal disruption. The field exerts magnetic pressure, pushing outward and balancing the inward pull of gravity or the stretching force of tidal fields. Webb cannot directly measure magnetic fields, but their presence can be inferred from the polarization of infrared light scattered by dust grains aligned with the field. Preliminary analysis of polarization data from MC12 suggests that a relatively strong field is present, supporting this hypothesis. Another possibility is that MC12 is more massive than it appears. If it contains a large amount of dark matter, or if its density distribution is more concentrated than models assume, it would have stronger self-gravity and be more resistant to tidal disruption. However, there is no direct evidence for such hidden mass, and invoking it raises more questions than it answers. The existence of cold molecular clouds near Sagittarius A-star has implications for star formation. If these clouds can collapse, they could form new generations of stars right in the immediate vicinity of the black hole. Some of the S-stars discussed earlier might have formed in this way, born from molecular clouds that collapsed within a few light years of Sagittarius A-star, despite the hostile conditions. The young stars would then remain in tight orbits around the black hole, surviving for millions of years until they eventually die or are disrupted. Webb searched for signs of ongoing star formation in the molecular clouds and found tantalizing hints. Several clouds contain compact infrared sources that could be protostars, young stellar objects still accreting material from their surroundings. The sources are embedded in the densest parts of the clouds, exactly where star formation theory predicts stars should form. However, confirming that these sources are truly protostars requires additional observations, particularly spectroscopy, to measure whether they are accreting and whether they have the temperatures and densities characteristic of collapsing cores. If star formation is occurring in these clouds, it would answer the long-standing puzzle of how the S-stars formed. Instead of migrating inward from greater distances or forming in a massive disk billions of years ago, they could be forming continuously from molecular clouds that survive in the galactic center. This would make the S-star population much younger on average and would provide a steady supply of new stars to replace those that are disrupted or ejected. The molecular clouds also affect the accretion flow onto Sagittarius A-star. When a cloud passes close to the black hole, tidal forces can strip gas from the cloud and inject it into the accretion disk. This process is not continuous but episodic, occurring whenever a cloud happens to wander close enough. The G2 cloud, discussed earlier, is an example of such an event, though G2 survived largely intact. Other clouds might not be so lucky, completely disrupted and feeding the black hole with a burst of material that causes a temporary increase in activity. The paradox of the cold molecular clouds is gradually being resolved as Webb provides more detailed observations. The clouds survive through a combination of shielding, magnetic support, and possibly self-gravity, maintaining cold, molecular interiors despite the harsh external environment. They represent reservoirs of material that could feed future star formation or accretion onto the black hole, and their presence indicates that the galactic center is not a completely hostile desert, but a complex ecosystem where different phases of gas coexist and interact. When light bends around darkness. One of the most striking predictions of general relativity is that light does not travel in straight lines near massive objects. Mass warps space-time, and light follows the curvature of space-time, bending its path. Near a black hole, this effect becomes extreme. Light passing close to the event horizon can be bent by 90 degrees or more, curving around the black hole and potentially making multiple orbits before either escaping or falling in. This gravitational lensing creates optical illusions, magnifying, distorting, and duplicating images of background objects. Webb's observations of the region around Sagittarius A-star revealed several instances of gravitational lensing, providing direct visual evidence of space-time curvature near the black hole. The most dramatic example involves a background star located directly behind Sagittarius A-star as seen from Earth. As the star moves through its orbit around the galaxy, it occasionally passes behind the black hole from our perspective. When this happens, the black hole's gravity bends the star's light around itself, creating multiple images of the star on opposite sides of the black hole. This phenomenon, called Einstein ring formation or gravitational lensing, was predicted in the early 20th century, but has only recently become observable at the galactic center due to improvements in telescope resolution and sensitivity. Webb's infrared capabilities allowed it to detect the lensed images despite the bright foreground emission from the accretion disk. The star, designated LS1 for lensed star 1, appeared as two distinct points of light on either side of Sagittarius A-star, separated by an angle of about 50 microarcseconds. The two images have different brightnesses because the lensing is not perfectly symmetric, with one image magnified more than the other due to the specific geometry of the alignment. By measuring the positions and brightnesses of the lensed images as LS1 moves through its orbit, astronomers can test general relativity in the strong field regime near the black hole. The theory predicts exactly how the images should appear and evolve based on the mass of the black hole and the geometry of space-time around it. Any deviations from these predictions would indicate that general relativity is incomplete or incorrect in extreme gravitational fields. So far, the observations match predictions perfectly, providing one of the most stringent tests of the theory ever conducted. Webb also detected microlensing events, where a foreground object passes in front of a more distant star, temporarily magnifying its brightness. These events are common in the galactic center due to the high density of stars. The light curve, how the star's brightness changes over time, provides information about the mass of the lensing object and its motion. Most microlensing events are caused by ordinary stars, but occasionally the lensing object is something more exotic, such as a black hole, neutron star, or rogue planet. One microlensing event detected by Webb had an unusual light curve that could not be explained by a single lensing object. The magnification pattern suggested the presence of two objects, a binary system passing in front of the background star. The masses inferred from the lensing were consistent with a pair of stellar mass black holes orbiting each other, a rare and valuable discovery. Binary black holes are the progenitors of the gravitational wave signals detected by LIGO and Virgo, and finding them before they merge provides insights into how they form and evolve. The lensing observations also revealed the mass distribution around Sagittarius A-star. By analysing multiple lensing events and the deflection of light from various background sources, astronomers can map the gravitational potential in the region. This is similar to how dark matter halos around galaxies are mapped through gravitational lensing of distant galaxies. Near Sagittarius A-star, the technique provides constraints on how mass is distributed, whether concentrated in a few massive objects or spread out among many smaller objects. One surprising result from this analysis is that the mass distribution appears more clumpy than expected. There are regions with higher than average gravitational deflection, suggesting concentrations of mass that could be dense star clusters, clouds of dark matter, or populations of compact objects like black holes and neutron stars. Identifying the nature of these clumps requires additional observations, but their existence indicates that the galactic center is even more structured and complex than models predicted. Gravitational lensing by Sagittarius A-star also affects how we observe the accretion disk itself. Light from the backside of the disk is bent around the black hole, allowing us to see regions that would otherwise be hidden behind the event horizon. This effect, combined with the Doppler shifts from the disk's rotation, creates complex emission patterns that make the disk appear asymmetric even if the underlying structure is symmetric. Modelling these lensing effects is essential for correctly interpreting observations and inferring the true properties of the accretion flow. Webb's high-resolution imaging is beginning to resolve some of these lensing effects directly. In certain infrared wavelengths, emission from the far side of the disk is visible as a faint arc wrapping around the black hole's shadow. This arc is the lensed image of the disk's backside, light that travelled most of the way around the black hole before reaching us. Measuring the brightness and spectrum of this arc provides information about conditions on the far side of the disk, regions that would otherwise be completely inaccessible to observation. The study of gravitational lensing near Sagittarius A-star is still in its early stages, but Webb's capabilities are transforming it from a theoretical curiosity into a practical observational tool. Each lensing event provides a new test of general relativity, a new constraint on the mass distribution near the black hole, and a new window into the complex environment surrounding the event horizon. As more events are detected and analysed, our understanding of how gravity behaves in the most extreme conditions will continue to improve. The black hole's influence on the entire galaxy. Sagittarius. A star is not an isolated object. Its gravity and energy output affect the entire galaxy, shaping the distribution of stars and gas, regulating star formation, and influencing the chemical evolution of the galactic center. Webb's wide-field imaging allowed astronomers to study these large-scale effects, revealing how a single object, despite being tiny compared to the galaxy as a whole, can have profound consequences for the evolution of the system in which it resides. One of the most significant effects is the suppression of star formation in the immediate vicinity of the black hole. Despite the presence of large amounts of gas, star formation rates within a few hundred light-years of Sagittarius A-star are lower than in other regions of the galaxy with similar gas densities. The reason is that the gas is too hot and too turbulent to collapse and form stars efficiently. The black hole's radiation heats the gas, and the jets and winds discussed earlier inject energy and momentum, stirring the gas and preventing it from cooling and fragmenting. Webb's observations quantified this effect by mapping the distribution of star-forming regions across the galactic center. Young stars and protostars are most abundant at distances greater than 300 light-years from Sagittarius A-star, where the black hole's influence weakens and gas can cool more efficiently. Closer in, star formation is sparse, confined to a few exceptional locations where particularly dense clouds have managed to collapse despite the hostile environment. The boundary at roughly 300 light-years marks a transition zone between the black hole-dominated inner region and the star-forming outer region. This suppression of star formation has consequences for the long-term evolution of the galaxy. The galactic center should be one of the most active star-forming regions, given its high gas density and favorable gravitational conditions. But the presence of the black hole limits this activity, preventing the center from converting its gas into stars as efficiently as other regions. Over billions of years, this effect accumulates, altering the stellar population and chemical composition of the central region compared to what would exist without a black hole. Sagittarius A also affects the orbits of stars throughout the inner galaxy. Its gravity creates a deep potential well that influences stellar motions out to distances of thousands of light-years. Stars orbiting through the galactic center experience gravitational perturbations that can change their orbits, sending them onto new trajectories. Some stars are accelerated and flung outward, while others are decelerated and drawn closer to the center. This dynamical mixing redistributes stars and gradually changes the structure of the central bulge. Webb detected evidence for this mixing in the form of stars with unusual orbits. Some stars in the galactic bulge, hundreds of light-years from Sagittarius A-star, are moving on highly eccentric or inclined orbits that cannot be explained by the smooth gravitational potential of the bulge alone. These stars likely experience close encounters with the black hole or with the dense star clusters near the center, receiving gravitational kicks that altered their paths. By studying the distribution of these unusual orbits, astronomers can reconstruct the dynamical history of the galactic center and estimate how often such encounters occur. The black hole's jets and winds also affect the galaxy on large scales. The Fermi bubbles discussed earlier extend thousands of light-years above and below the galactic disk, carrying energy and material far from the galactic center. As these outflows expand, they interact with gas in the galactic halo, heating it and possibly preventing it from falling back onto the disk. This process, called feedback, regulates the growth of the galaxy by limiting how much fresh gas is available for star formation. Without feedback from Sagittarius A-star, the Milky Way might have formed stars more rapidly and exhausted its gas supply billions of years ago. Webb's infrared observations of the base of the Fermi bubbles revealed the connection between the black hole and the large-scale outflows. The gas at the interface between the bubbles and the disk is heated to millions of degrees, emitting in X-rays, but it also contains cooler material emitting in infrared. This cooler material consists of dust and molecular gas, entrained by the outflow and carried upward. Webb measured the velocity of this material, finding it is moving at hundreds of kilometers per second, fast enough to escape the galactic disk and enter the halo. The chemical composition of the gas in the outflows is also revealing. It is enriched with heavy elements, particularly oxygen, nitrogen and carbon, indicating it originated from star-forming regions or supernova remnants. This means the outflow is not just carrying energy, but also redistributing heavy elements from the galactic center to the halo. Over time, this process enriches the halo with metals, altering its chemical composition and potentially affecting the properties of halo stars and any subsequent star formation that occurs there. Sagittarius A's influence extends even to the spiral arms of the Milky Way. The gravitational potential created by the black hole and the central bulge helps maintain the stability of the spiral pattern. Perturbations from the black hole can see density waves that propagate outward through the disk, reinforcing the spiral arms or creating new ones. While the black hole is not the sole driver of the spiral structure, it plays a supporting role, contributing to the overall dynamics that shape the galaxy's appearance. Webb's observations of the galactic center in context with the broader galaxy provide a holistic view of how supermassive black holes influence their host galaxies. Sagittarius A-star is not just a passive resident at the center. It is an active participant in the galaxy's evolution, regulating star formation, redistributing matter and energy, and shaping the dynamics of stars and gas across vast scales. Understanding this interplay between black holes and galaxies is crucial for understanding how galaxies form and evolve throughout the universe. The race against time and radiation. Webb's observations of Sagittarius A-star are not just scientifically valuable, they are historically significant, capturing a black hole during a specific phase of its life that may not last much longer. The evidence suggests Sagittarius A-star is transitioning from a dormant state to a more active one, and if this trend continues, the black hole we observe today will be very different from the one future generation study. This realization has created a sense of urgency among astronomers, a race against time to document the current state before it changes irreversibly. The signs of increasing activity are numerous. The elevated X-ray emission that began in 2006 has not returned to previous baseline levels. The flare frequency has increased. The jets, weak as they are, appear stronger now than in observations from the 1990s and early 2000s. The spiral in the accretion disk is intensifying, and the hot ring detected by Webb was not present in earlier Spitzer observations, suggesting it formed relatively recently. All of these changes point toward a black hole waking up, transitioning from a quiet phase to something more energetic. If Sagittarius A-star does become significantly more active, the consequences for observations will be profound. A brighter black hole will be easier to study in some ways, with stronger emission across all wavelengths providing more signal for instruments to detect. But increased activity also brings challenges. Variability will become more extreme, with the black hole flickering on shorter timescales and making stable imaging difficult. Outflows and jets might strengthen, creating additional emission that obscures the innermost regions. The accretion disk might thicken and become more optically opaque, hiding the event horizon's shadow behind a wall of hot gas. Webb's current observations are capturing Sagittarius A-star at a pivotal moment. The black hole is more active than it has been in living memory, but still not so active that its emission dominates over all other structures. This balance allows astronomers to study both the black hole itself and its surrounding environment, seeing how they interact and influence each other. If activity increases significantly, this balance will be lost, and certain types of observations will become impossible or require fundamentally different techniques. The timeline for this transition is uncertain. If the accretion rate continues increasing at its current pace, Sagittarius A-star could become 10 times brighter within a decade or two. That would make it one of the brightest objects in the galactic center, easily outshining nearby stars and requiring adjustments to how telescopes observe the region to avoid detector saturation. Alternatively, the current increase might plateau or even reverse, with the black hole settling into a new equilibrium at slightly higher activity than before, but not undergoing a dramatic transformation. Part of the uncertainty stems from not knowing what is driving the increased activity. If it is due to the gradual infall of material from disrupted clouds or stellar winds, the process could continue for millions of years at a slowly increasing rate. If it is triggered by a specific event, such as the tidal disruption of a star that has not yet been completed, activity could spike dramatically when the bulk of the stellar debris finally reaches the black hole, then decline again afterward. Without knowing the cause, predicting the future is speculative. Webb's role in this race is to document as much as possible while conditions remain favourable. Every observation adds to the archive of data that will be invaluable for future studies. When Sagittarius A-star does change, astronomers will compare the future state to Webb's current observations, using the differences to understand how black holes transition between different activity levels and what physical processes drive those transitions. There is also the matter of radiation damage to Webb itself. The Space Telescope operates in a harsh environment, constantly bombarded by cosmic rays and high-energy particles. Over time, these particles degrade the detectors, creating hot pixels and reducing sensitivity. Webb was designed to last at least 10 years, with hopes for extended operations beyond that. But there are no guarantees. If a major solar flare or cosmic ray event damages critical components, Webb's ability to observe faint infrared sources, like the galactic center, could be compromised or lost entirely. The urgency is compounded by the fact that no other telescope currently operational has Webb's combination of sensitivity, resolution, and infrared capability. Hubble, while still functional, cannot see through the dust enshrouding Sagittarius A-star. Ground-based infrared telescopes lack Webb's resolution and are hampered by atmospheric absorption. Future missions, such as the Nancy Grace Roman Space Telescope, or even more advanced concepts, will not launch for years or decades. If Webb were lost before those missions come online, a gap in our ability to study the galactic center at these wavelengths would open, potentially lasting a decade or more. This race against time adds emotional weight to Webb's scientific mission. Every successful observation feels like a victory, a piece of knowledge secured before the opportunity vanishes. Every technical glitch or scheduling conflict represents lost time that cannot be recovered. Astronomers working on galactic center observations are acutely aware that they are documenting a transient phase in the life of our galaxy's central black hole, a phase that future scientists will look back on as a historical moment in the black hole's evolution. The data Webb is collecting now will be studied for decades, possibly centuries. Future generations of astronomers will mine these observations for insights, using analysis techniques and theoretical frameworks that do not yet exist. They will ask questions we have not thought to ask, finding patterns and correlations that elude current researchers. Webb's observations are not just answering today's questions. They are creating a resource for future science, a time capsule of data capturing Sagittarius A-star at a specific moment in its billions-year-long existence. The waking galactic black hole. The James Webb Space Telescope has transformed our understanding of Sagittarius A-star, revealing it to be far more complex, active, and mysterious than anyone anticipated. The black hole at the center of our galaxy is not a quiet, dormant object, patiently waiting in the darkness. It is a dynamic, evolving system that is changing on timescales we can measure, transitioning toward a more active state that could reshape the entire galactic center over the coming millennia. Webb's discoveries have raised as many questions as they have answered. The spiral in the accretion disk, the hot ring of particle acceleration, the hidden jets, the molecular clouds surviving in hostile conditions, the rogue planets orbiting the black hole, and the possibility of a companion object all represent puzzles that will occupy researchers for years to come. Each discovery demands new theoretical models, new observations, and new ways of thinking about how black holes interact with their environments. What terrifies scientists is not just the complexity uncovered by Webb's observations, it is the realization that Sagittarius A-star is waking up. The increasing activity, the intensifying spiral, the elevated X-ray emission, these are signs of a black hole entering a new phase. If the trend continues, the quiet monster at our galaxy's heart will become loud, blasting the surrounding region with radiation and jets that could suppress star formation, heat the galactic center, and fundamentally alter the environment for millions of years. We are witnessing the beginning of this transformation, observing in real time as a supermassive black hole transitions from dormancy to activity. And the most unsettling truth is that we are helpless to stop it. Sagittarius A-star operates on timescales and energies far beyond human influence. We can only watch, measure, and try to understand as our galaxy's central black hole reveals itself in ways we never imagined possible. The James Webb Space Telescope has given us eyes to see this cosmic drama unfolding. But what comes next is beyond our control, a reminder that we are observers in a universe far more powerful and unpredictable than we can ever fully comprehend.